A very good morning to one and all. On behalf of the Institution of Engineers India, I welcome you to the third technical session of the 34th National Convention of Metallurgical and Materials Engineers and the National Conference on Sustainability and Steel Industry. It is being organized in virtual mode by Jharkhand State Center of the institution. We are having with us Mr. D.K. Ambassador, Chief General Manager, Mekon Ranchi, as the session chair, and Mr. M.R. Kumar, Senior General Manager, Mekon Ranchi, as the rapporteur. In this session, we are going to have 6 papers to be presented from CMPDI Ranchi, CET Cell, Tata Steel Jamshedpur, and the Energy and Resources Institute, ISP Banpur Cell, and from IMT Bhubaneswar. We are having with us Mrs. Abha Prasad, who is going to present the first paper. Then followed by this, then it will be followed by the second paper, Mr. Anand Trivedi. Mr. Anand Trivedi has informed that he is traveling now, so he will be joining. He may be late for a couple of minutes. So in that case, we may go ahead with the third paper, sir. So now I would request you to take over, request the session chair to take over. Thank you, sir.
Good morning, everybody.
Morning.
It's a very important session and very important topics, that is sustainability in the steel sector. And all the participants are with the relevant experience and in the field. So I hope the session will be very lively and interactive. We have got sufficient time, and adequate time will be available to present the paper, and we can have some interaction also. So with me, Mr. M.R. Kumar is there. He can start. Mr. M.R. Kumar.
Sir. Yeah. Good morning, Chairman sir. The biodata of Chairman sir is like this. Sri D.K. Ambassador, Chief General Manager, Steel Making. He graduated in Mechanical Engineering in 1984 from NIT Jamshedpur. He did ME MTech NIT Rourkela, and with MBA IGNO. He has received award of excellence in Mecon from IIM. His experience spanned from 1985, joined in Mecon as MTT. He got more than 35 years of service in Mecon with the design and engineering of various projects, particularly in the area of hot metal desulfurization, steel making, refining, and continuous casting. Worked in various projects of integrated steel plants like SAIL units, RINL, JSPL, and JSW. With this, thanks, sir, Chairman, sir. We will start with the first paper, just augmentation of coking coal for steel sector.
So how much time we are giving to all the papers?
Sir, 12 minutes will be given for the presentation, and 3 minutes we will have a question answer session after completion of the presentation, sir.
Okay, fine.
So I request Abha ma'am to start the presentation on paper, ma'am.
Good morning, everybody. I am Abha Prasad, Chief.
Ma'am, I would request you to stick to 12 minutes for your presentation, and let us have the 3 minutes for interactive session. And I am requesting all the panelists to stick to the schedule we are giving you so that we can smoothly complete the session. Thank you.
So first, I'll right away start with the presentation.
Mm-hmm.
Slide. नहीं full screen आता है. Are you able to see the presentation?
Yeah. Continue, ma'am.
So first of all, I am thankful to Institution of Engineers for giving me the opportunity for presentation of this paper on the 34th National Convention. The paper is augmentation of coking coal for steel sector. I will be presenting this on behalf of our CMD CMPDI Shri Manoj Kumar and our GM CMP Shri Pushparaj Verma. So we all know that coking coal is a critical input in metallurgical industry, especially in steel industry, and it serves mainly three functions. It serves as a fuel to provide heat for chemical reactions, as a reducing agent, and to support the charge of the burden in the furnace. But because of the scarcity of good quality indigenous metallurgical coal, import of coking coal in India has been showing an increasing trend, and this is resulting in high outflow of foreign exchange. In 2021, the total coal imports of the country was about 215 million ton, out of which 51 million ton was imported coking coal, and the rest was non-coking coal, and it led to an outflow of about 11.6 lakh crores from the country's economy, which is a huge amount. As such, there is an urgent need to restrict import of coking coal by augmentation of production of coking coal in the country. So these are the coking coal resource of India as per GSI. We are having 35.1 billion ton of coking coal reserves.
मैम स्क्रीन चलाइएगा, फर्स्ट स्क्रीन में है. Go to next slide.
Yes, I have.
Okay.
Wait, I have changed the slide.
Madam, you do one thing. You run it in standard mode instead of this one, by presentation mode. You run it in standard mode. That will help you. Okay. The presentation mode is always giving trouble. Okay, just change it to standard mode. Then you just run your presentation.
Yes, ma'am. You please stop sharing once and then try to share it again. Then it will run.
Is it visible now? Next
Yeah,
present.
yeah.
Visible. Visible.
Yes.
Yes.
Visible.
So we are having 35.1 billion ton of coking coal reserves, out of which about 80% is medium coking and only 15% is prime coking. And semi-coking coal, we are having only 4.87 percentage reserves. Out of this, 57.5 is proved reserves. So out of this, the 35.1 billion ton of coal reserves, 18.83 coal reserves lies with CIL blocks, 9.63 with non-CIL blocks, and the rest 6.54 lies with others like Tata Steel, SAIL, and deep-seated resources in Jharia, East Bokaro coalfield, and West Bokaro coalfield.
Yeah.
Talking about the coking coal in India, we all know because of the drift origin, Indian coking coal is having high ash content and making it difficult to wash at reasonable yield. It also contains less reactive vitrinite and liptinite material needed to produce good coke. It is generally of poor caking and coking properties in terms of FSI coke type rank, and therefore it produces coke of high ash and poor strength parameters. Because of these reasons, it needs to be blended with superior quality coking coal to produce coke of desirable properties suitable for use in steel making through blast furnace route. As per the projection of coking coal in CIL in the year 2930, we can see here that the majority of the reserves, about 50% is having of washery grade 4, having an ash range of 28 to 35, and about 25% is of washery grade 5, 35 to 42%, and only a very small proportion is of semi-coking coal. As per the National Steel Policy in 2017, India is expected to build a capacity of 300 million ton of steel per annum, and about 60%, that is 181 million ton, will be through the blast furnace route, for which 161 million ton per annum coal of coking coal having an ash of about 10 to 11% will be required. For PCI, non-coking coal having good quality 8 to 10% ash is required, which is 31 million ton. And for through the DRI process, good quality non-coking coal of 105 million ton per annum will be required. So when we for coke making, what is the requirement of coal quality? Among other parameters, ash, which is it should be less than 11.5, and mean maximum reflectance is in the range of 1.15 to 1.19. And mean maximum reflectance is a property which is independent of washing, and it has a direct correlation with the coke reactivity index, which should be less than 25 in the coke, and coke strength after reaction, it should be more than 55. This parameter is very important for coke making. When we come to the imported coking coal specifications, the ash is about 8 to 10%, and MMR ranges from, for the hard coking coal, 1.15 to 1.35, having an average of 1.25. If we look at the consumption of clean coal by SAIL in last 10 years, we see that SAIL had been blending 25% of indigenous coking coal with imported 75% of imported coking coal to meet its requirement. But gradually the percentage has gone down to 10%, and mostly because the washeries of BCCL and CCCL, they have not been able to produce so much because of aging, and also because they were designed for washery grade 2 and 3, but they are not able to get the designed raw coal quality. We have worked out the average blending ratio based on MMR. So if we take the average of MMR of hard coal, it is 1.25, and for the indigenous coking coal, it is 0.93 based on the test results of 19 samples. So we have back calculated to achieve the MMR ratio of 1.174, which is required for the coal blend. It works out to 75% of imported coal and with 25% of indigenous coking coal. And using this same ratio and have ash of imported coal in the range of 8 to 9% and indigenous coal between the 17 to 20%, that is 18.5% ash, we see that a coal blend of 11% ash can be achieved. So we need not go around below 18% for the meeting this requirement. And one parameter is important that I've already said, that 1.15, if the MMR goes below 1.15, then the coke which is produced is of poor quality, and that which causes detrimental effect in the blast furnace. So one method of improving the blending ratio is by stamp charging, in which the coal is first pressed mechanically, which increases the bulk density of the coal charge and before feeding into the coke ovens. And this increases the CSR and reduces the CRI values. And with the help of stamp charging, we are able to use a larger proportion of inferior quality coking coal. Tata Steel is currently blending about 68 to 70% imported coking coal with 30 to 32% of domestic clean coal. So that the ash percentage of coal blend is less than 13%, whereas in case of SAIL, it is less than 11.5%. So it is able to produce blend more. SAIL is not using stamp charging technology presently. So this is the three scenarios which have been worked out. If we don't go for stamp charging, we can blend at least 25% of indigenous coking coal having an ash of 18.5 with the imported hard coal with having an ash of 8.5. With stamp charging, this blending ratio can be increased from 25 to 35 to get an average of coal blend of 11.5. And currently Tata Steel is blending 30% of indigenous coking coal having 18.5 with 70% having 10% ash to get a coal blend of 13%, around 13% ash. So what is the strategy to meet the requirement of washed coking coal by 2930? We have, and CIL has envisaged a number of washeries in both BCCL and CCL. 3 washeries in CCL are already in operation, and only these Rajrappa and Kathara, they will be replaced by new washeries, and only Kedla, having an operable capacity of 1.3, will be on operation by 2930, from which we will be able to get 0.4 million ton in coal. CCL has proposed 6 washeries, out of which New Kathara and for Basantpur Tapun, the LOI has already been issued in March 19, but because of the NOC for transfer of CBA land to Blue Operator from MOC, it is awaited. So the construction of these washeries could not be started. For New Rajrappa, the tender will be floated after competent approval, and only tomorrow first there will be a meeting regarding this. And for Dhori and New Swang, the infrastructure facilities have already been finalized, and washability testing is to be done. And after that, we can proceed with this. We'll take up this project. For Topa washery, the earlier land which was identified was not found to be suitable. So this is pending due to finalization of land and is likely to be finalized soon. So from CCL, we'll be able to get about 8.74 million ton from the existing Kedla washery and from the new 6 proposed washeries of CCL on BOO concept. When we come to BCCL, BCCL is having 6 washeries in operation, out of which Dahibari having a capacity of 1.6 is in operation since August 2018, and Pa31 having a capacity of 5 MTY is under operation since July 2020. And BCCL is planning to renovate these washeries either on the turnkey concept or renovate, operate and maintain concept, in which in this ROM concept, the funding will be provided by the bidder. So Madhuban will be taken up as the first, and if it is successful, the same the renovation of Dudha 2 and Mahda will be carried out. So we can get a clean coal of about 18 to 19%, 4.17 million ton from these 6 washeries. 3 more washeries under the build, operate, maintain concept are under construction, and because of the COVID pandemic, the construction has been affected. So, now it has picked up, and Madhuban washery was recently inaugurated on 24th March. And for Munity new washery on BOM concept, the price bid has been opened on 24th March. All the washeries of BCCL and CCL, they have been planned for getting clean coal at 18 or 19%, except Munity because it is prime coking coal and the raw coal is of washery grade 2. So we have planned it for 14% clean coal. And these are the coking coal washeries of Tata Steel. Tata Steel is having a capacity of 10 MTY washing capacity from its 4 washeries, and SAIL is having 1 existing washery, Chasnala, and Thasra of 4 MTY has been proposed. So when we come to the scenario of washing capacity in 29-30, we see that we can get about 80 million ton of clean coal from 45 million ton of raw coal washing capacity, and assuming about 50% yield from both SAIL and Tata Steel washeries, from 16 million ton, we can get 8 million ton. So approximately 26 million ton of clean coal having 18 to 19% ash, and for Munity, of course, 14% clean coal will be available. So the requirement which was as per the national steel policy was 161 million ton. And if we don't go for stamp charging, then 25% can be blended. So 40 million ton of indigenous coking coal will be required at 18.5% ash. And if we go for stamp charging, then 56 million ton of indigenous coking coal will be required, for which assuming a very conservative yield of washed coal, we have worked out that 120 million ton washing capacity will be required if we go without stamp charging. And if we go for stamp charging, then 170 million ton of washing capacity will be required. So out of this, 60 million ton washing capacity has already been planned. So it will lead to a reduction in the import of coal. So from 121 to 105 million ton. So
I would request you to sum up, please.
Yes, it is just, I'm just ending the presentation. So we have planned the raw coking coal projections from coal, taking Coal India, SAIL and Tata Steel. The production projection is about 150 million ton, and rest can be met from the blocks already allocated with having a PRC of 29.14, and from Coal India PRs 9.63. So we have having about 170 million ton projections have already been done. So we are having additional requirement of clean coal is 14 million ton if you go without stamp charging, and if you go for stamp charging, that is 30 million ton. And this is the strategy for meeting. We can additional washed coking coal can be met through planning of additional coking coal washeries by CIL or by Tata Steel and SAIL, or by other steel companies with coal source from CIL mines through linkages, or through coal blocks allocated to them, or any other entity interested in coal washing business with coal source from CIL coal block allocatees. Thank you.
Thank you, ma'am. I think second paper, energy recovery through TRT for sustainable iron making. Mr. Anand Trivedi is not joined so far.
Yes, Mr. Anand Trivedi has not joined yet, so we can move ahead with the third paper.
Yeah. The third paper comes from Tata Steel. circularity as a solution to tackle resource challenges in steel industry. This will be presented by Dr. Hashmi Jamal Hussain. Saab hai?
Yeah, good morning.
Yeah. Welcome.
So good morning to all. Thank you to the organizer for giving us opportunity to present on the circular economy. And indeed, if you want to achieve the sustainability, we should think about the circularity. And circularity is the mantra of success of sustainability. So my colleague Rajita is with me and she will share the presentation. Over to you, Rajita.
Thank you, sir. So I have shared the presentation. Hope it's visible.
Yes, it is visible.
Good morning, everyone. So we'll be doing the paper presentation on circularity as a solution to tackle resource challenges in the steel industry with Tata Steel India as a case example. So this is the agenda for today. To set a basic background, it has been reported in a World Economic Forum report that if the current world follows the current linear trajectory of development globally, 4.5 trillion US dollars would be at stake by 2030. And the linear development trajectory, when I talk about it, it means the take, make, discard model, which doesn't account for recycling, reusing, or reducing the waste or the material that is generated. So this model basically, when we are talking in the context of mining commodities, mining metal commodities especially, so this increases the exposure of these commodities and the organizations which are dependent on these commodities to risks such as volatility in raw material prices, disruptions in supply, and increase in the extraction cost, to list some of the risks. Now, mined metal commodity production in going ahead by 2030 is expected to jump to 250%, and the demand specifically for iron is expected to grow at 86% rate by 2050 and 100% by the end of this century, that is 2100. And this will result in significant increase across the value chain from extraction to waste generation activities, significant increase in the waste production, as well as resource exploitation. So moving ahead, when we see the value chain of steel value chain, so these are the major points in the steel value chain where waste is generated, and the darkly colored ones, the extensions and the extraction part, the processing part, is where the highest volume of waste is generated. After that, in the manufacturing of the steel, that is where next highest amount of volume of waste is generated. After that, logistics, engineering and design, and consumer use is where it is comparatively lower, but still in all these places the waste is generated. So when we are going towards circularity, we have to keep in mind that these are the points at which the waste, the processes has to be designed in a way that this whatever waste is being generated, it can be reduced. So coming to the point of circular economy, what opportunities India presents? So circular economy model can reduce the consumption of virgin non-renewable materials by 38% in 2050 if this model is followed. And following circular economy strategies will help Indian economy to reduce greenhouse gas emissions by 44% by 2050. And it could bring around 40 lakh crores in economical benefits to India by 2050, in addition to reducing any of the negative externalities that is being generated. So what are the benefits the following circular economy can give to India is, it can increase household disposable income through lower cost for products and services. Then it can provide profit opportunities and material cost savings for the businesses. It can lower the use of virgin materials such as water and artificial fertilizers and the metals even. Then it can reduce traffic congestion, air pollution. Apart from that, advantages can be taken of the impending digital revolution achieving the circular economy, and it will reinforce India's position as hub for innovation and technology. So coming to circularity in the steel industry. So steel industry is most conducive to adoption of circular economy model because steel is recyclable at the end of life. So it is considered one of the pure materials. As you can see in the diagram, by the end of the life cycle, whatever scrap is generated, it can go back to the processing and reused n number of times. Now, since 1900, the global steel industry has recycled over 22 billion tons of steel, and this has reduced iron ore consumption by 28 billion tons and coal consumption by 14 billion tons. The industry has also reduced the use of energy by almost since 1960, 40% of the energy that was previously required for steel production has been reduced. Apart from that, the waste generation has also been taken care of. Now, working with other external partners, the industry has been able to find markets for over 97% of its waste production, and now around only 2.7% of waste stream is generated. So Tata Steel also has a byproduct and waste management division. We'll be talking about it in the later slides. So what exactly is the circular economy model? So circular economy model is a regenerative and restorative industrial. I'm talking about this in the context of industry. So basically it's an industrial system by design which replaces the end of life concept with restoration, and it shifts towards the use of renewable energy, eliminates the use of toxic chemicals which impair reuse and return to the biosphere, and aims for elimination of waste through the superior design of materials, products, systems, and business models. So these are some of the things which we have incorporated in our business model as well. So the four foundational principles for industrial circularity are: number one is the design out the waste. So the processes or the products are designed in such a way that the waste is reduced or totally removed from the process. Then differentiation between consumable and durable products. So the consumables, it is taken care that they should be of biological in nature and they become part of the nature once used. Then the durable products are made in such a way that they can be they are known as the technical nutrients, and these durable products can be used in such a way are produced in such a way that they can be reused and recycled for n number of times, so that they don't generate waste. Then renewable energy can be used as a fuel to drive the circularity. Also replace the concept of consumer with user. So rather than consuming it and discarding it, you become the user of it. You share the whatever product or is produced, you share it with others as well. Now, what is the business case for adoption of circularity? So the circular economy model creates sources of value creation through minimizing comparative materials use, maximizing the number of consecutive cycles, diversifying the reuse across the value chain, and increasing collection and redistribution efficiency for pure metals such as steel. So now we'll come on to the Tata Steel. So this is a little bit about Tata Steel. I'll just quickly go through it. We are a multinational steelmaking company, a subsidiary of Tata Group, founded in 1907. Currently, we are producing 34 million tons of annual crude steel capacity, and we are geographically diversified with operations in 26 countries and commercial presence in 50 countries. We cater to automotive construction, consumer goods, engineering, packaging, excavation, energy powered industry, shipbuilding, rail, and security sectors as well. And the company produces iron, soft iron, cast iron, alloy bearings, and the rest. Yeah. So this is the basic introduction. Now coming to the major point, that is the circularity in Tata Steel, how we are manufacturing. So Tata Steel operates highly efficient steel works, achieving high material yields by consuming residues arising in the processes, finding high value uses in other sectors for its byproducts, and acting as a recycler for the residues of other sectors of the economy. And these are some of the major cases in which the circularity is getting manifested in Tata Steel. I will take you through them one by one. The first one is the integrated steelwork. So as you know, our plants are integrated, and when we have all the the main raw materials for integrated steel making are iron ore, steel scrap, coal, coke, limestone, and dolomite. So approximately 2 tons of raw material is required for casting 1 ton of cast steel. And this cost of raw materials as well as the energy, it is a major cost base for the steel industry. And as we are going ahead, the competitiveness demands that resources should be used efficiently. So keeping that in mind, as well as the requirement of the circular economy principles, these integrated steelworks have been developed around the model of recirculation of materials, energy, and water across the individual components. So this picture shows the example of the coke oven, blast furnace, and converter gas, which gets reused across the steel plant and we are able to get this advantage because of it being integrated. The second initiative is the Steel Recycling Business Initiative by Tata Steel. So whatever scrap is getting produced, that gets recycled. So it has been documented that the steel produced through recycled route entails significantly lower carbon emissions, that is approximately 63% lower, and 68% lower resource consumption, and 58% lower energy utilization. So this initiative aims to provide much needed raw material to steel industry by making available quality processed ferrous scrap, streamlining the currently unorganized scrap supply chain. So this plant has been, the first plant has been set up in Rohtak, Haryana, with 0.5 million ton capacity in September 2020. And it has all the mechanized equipment such as shredder, baler, material handler for processing and handling, as well as producing the top quality scrap. They have also come up with first of its kind brands called Tata Ferro Build and Tata Ferro Shred. Apart from that, an app has also been launched known as Ferro Heart. Basically, it sources the steel scrap from traders. So we have introduced a digital app as well in our circular economy initiative. The next initiative is our byproduct management. So we have a separate marketing division called Industrial Byproduct Management Division, which manages the byproducts and scrap generated across the steel value chain. So we are producing Tata Agrito and Tata Nirman, the two brands from the LD slag, and this is being used for construction of the national highways. And this invention relates to a process for curing of steel making slag, including reduction of free alkaline earth oxide with volume expansion less than 2% using steam at variable conditions for pressure and temperature. So basically, this is a faster process, and it creates, generates value from the waste that has been created.
Yeah, ma'am, please conclude.
The next project is the yes. So the next one is the Haisarna project. So it basically skips the coking and agglomeration requirement and directly goes to the iron making process. So this was piloted in the Europe, and now it is being brought to India as well. So it has been studied that around 80 to 90% of carbon dioxide reduction is seen when this Haisarna technology of steel production is combined with carbon capture and utilization process. Apart from that, we have also adopted the 4R strategy of the life cycle, and these are some of the initiatives that have been undertaken under this one. And the final one is utilizing steel plant WRP waste for after recovery of metallic iron. So whatever is left, we are making multi-nutrient sulphate fertilizer out of it. Yeah, so these are some of our initiatives of circular economy. Thank you so much.
Thank you, ma'am. Any questions on this presentation? Can we take?
Can you hear us?
Yeah. Mitra sir, boli.
I'm from Billard Steel Plant. I'm talking. Where you are going to bring this Haisarna project in India? I think right now it is at Netherlands.
Yes, sir. Yes, sir. Right now.
So where you are planning to bring it to in India? You just said that is you are planning to install that kind of project in India also.
Yes, sir. So it'll be soon. The project has been approved and it will soon come to India.
Okay. What are the techno-economics when you go through Hycerna project? How much that is in cost terms? How much saving you can make in making 1 ton of crude steel? Have you done that analysis? You have the data.
So are you talking in terms
of
cost?
Cost benefits, energy benefits, weight benefits, whatever it is.
So can I share that with you separately on your email?
Definitely, madam. I will be grateful. Okay.
Sure. Thank you.
Thank you. Thank you.
Yeah, any other question?
So we are getting couple of questions in the question answer tab.
Yeah. What about BF slag uses? That is the one question from Arvind Kumar Akela. And more question is BF slag can be used as LD slag application. That's what he is giving an information. Ma'am, what about BF slag use? What Tata Steel is doing? Can you elaborate on that?
So we are using all the slag in as a byproduct, and we are using in a construction material. So you perhaps know the road between Ranchi and Jamshedpur, it is built by the same slag. So it is a product called Agrito.
Correct.
So it is all made by BOF slag, right? What Mr. Hussain is telling? Yeah. So what he's telling, this Ranchi Tata road is made by BOF slag, LD slag. Is it correct?
Yeah. Yes.
Okay, but actual question is blast furnace slag. What they are doing in Tata Steel, sir? Blast furnace slag.
So Agrito product, I told about the product which has made called the Agrito. So Agrito is a product from that.
Okay. The details of CCS would be great interest, even international. Please give little more details. Okay, that we will share separately. I think Tata Steel, we will send that. I think then we can close this paper, and the next paper is exploring the potential role of hydrogen in the Indian steel sector. This presentation will be done by Mr. Girish Sethi.
Sorry to interrupt you in between. So Mr. Anand Trivedi has joined. So he is requesting for his staff. So
Okay, then
we can take his paper.
Yeah, that means we will take that from Mr. Anand Trivedi paper.
Yeah.
Thank you, sir. Thank you.
Thank you, Anand. This paper is on energy recovery through TRT for sustainable iron making.
Yes, sir.
Anand Trivedi from Set Sail Ranchi. You can start the presentation, Mr. Anand.
Sure, sir. Sir, is this screen visible to everyone?
Yeah.
Oh, thank you. Thank you, sir. And my apologies for the delay. Actually, I am on move. I have come to Rourkela and there is a meeting, so I just requested. And thanks for heeding to the request, sir. I welcome you all, everybody on board here in this presentation on energy recovery through TRT. TRT part is missed in this line for sustainable iron making. How this is relating with the seminar topic? Basically, our seminar is regarding sustainability in iron and steel production. And in iron and steel production, BF route still dominates the whole world. And as far as BF route is concerned, so far we understand that more or less 70% of the production of steel industry is through this route. So in this particular route, the main energy requirement is at the blast furnace itself. And when we see at the blast furnace is a system where we definitely insert our raw materials as well as coke to reduce it further and get iron, molten iron. In this particular process, the major role is also played by one thing which is known as hot blast, which is inserted through 2 years. And this hot blast, as we all know, is generated in turbo blowers. Turbo blowers are basically the kind of equipment which are more or less compressors in a parlance, that they compress my atmospheric air after filtering it, and then this atmospheric air after filtering it goes to turbo blowers. In more or less the earlier setup, these turbo blowers were driven by steam turbines, but slowly and gradually the electrical motors are now replacing steam turbines. Steam turbines usually get steam from boilers which are there nearby. Steam turbine had its own advantages, and now motors are also picking up, and they are having its different advantage. But now my topic of presentation is basically TRT. Why turbo blower I'm talking about? Because in the turbo blower, when we compress air, we require huge amount of power. Steam turbine gives that power to my compressor. Normally, if you talk about a 2000 meter cube blast furnace, then in such type of blast furnace, my turbo blower's energy requirement will be to the tune of 22 to 25 megawatt. So this 22 to 25 megawatt power is basically a part of energy which is being consumed in the blast furnace. So this is a major chunk of energy, and one of the things through which we can reduce this energy consumption is TRT. How it is that I'll explain in my presentation further. Now, since in blast furnace, once we reduce the components which we are putting it from the top, that means our iron ore as well as coke and everything, then whatever residual part of gases are there, they are coming at the top. And when these gases are coming at the top, they are having some impurities as well as, but the major important part for appreciating to others is that this gas is also having certain calorific value. That means this gas can be utilized for combustion purpose. Now the calorific value is low. Normally it is in the range of 800 kilocalories per nm cube. So this low calorific value gas is also utilized for burning in the boilers, as well as there are certain applications in coke ovens. That means we need this gas basically. So in older blast furnaces, this gas was earlier taken from the top, then it was cleaned in the gas cleaning plants. And after cleaning in the gas cleaning plant, this gas was used for combustion purpose. So this gas was available normally in the range of 0.5 to 1 bar at the top in earlier blast furnaces. And then after cleaning, the pressure was reduced because the blast furnace gas was distributed inside a steel plant in a pressure range of 400 to 800 millimeter water column. That means 0.04 to 0.08 bar gauge. So this was the earlier setup where we used to have the blast furnaces in the range of 1100 to 1500, even up to 2000 in some cases. But my top pressure was less. Less means it was in the range of 0.5 to 1. And this blast furnace gas was only cleaned and then it was used for combustion purpose. Then basically the setup was like this. The blower was feeding to the blast furnace the cold blast, and the product of combustion was coming at the top in the form of blast furnace gas. And then it was cleaned in the dust catcher or venturi scrubber, and then through septum valve the pressure was reduced, and then it was sent to system through a gas holder. But here after analyzing this particular thing, people felt that there is a saving potential. How the saving potential is there? Now the blast furnaces are bigger, they are of higher size, they generate high amount of iron ore. Normally in a 4,500 meter cube capacity of blast furnace, we generate 3 million tons per annum of iron per year. So with such type of blast furnace, the productivity of such furnaces are high. That means in the range of 2.5. And in these furnaces, the thing is that since we have to now gather more iron from the blast furnace, so we need more air for the reduction. And how can we give more air? By compressing it more. That means earlier when we used to supply the through turbo blower our coal blast, it was normally in the range of 1.5 to 2 bar gauge, and that was sufficient for combustion purpose in the blast furnace. But since now we are inserting more air in the blast furnace, the pressure at the 2 years means that this hot blast or this compressed air is being supplied in the pressure range of 3.5 to 4. That means at the top of the furnace, we are having higher pressure at of the blast furnace gas as well. So blast furnace gas in these bigger blast furnaces and newer blast furnaces is available at a pressure of 2 to 2.5 bar gauge. So this is a very good pressure in the sense that if a gas is available at this type of pressure, that means 2 to 2.5 bar gauge, and the volume of gas is huge, means it is in the range of 4 lakhs to 6 lakhs Nm cube per hour. This type of volume we are talking about, and when this type of volume is available at the pressure of 2.5, that means we have got the potential. And this higher volume and the higher pressure can be gainfully utilized for extracting power. Means we are not doing anything, we are just gathering we are just taking the advantage of its higher pressure, and we are putting this high pressure blast furnace gas after cleaning into the turbine. And this turbine is known as top pressure recovery turbine, TRT in short form. So what it does, so for a typical blast furnace of 4,005 meter cube capacity, when the gas is available at a pressure of 2.5 and the volume is in the range of 4 to 6,000 Nm cube per hour, then in this setup we extract almost 20 megawatt of power. That means whatever power we are giving in the blowers, some of it we are able to extract in the form of TRT, thereby reducing our overall power consumption in the blast furnace and increasing its energy efficiency as well as the potential for its future sustainability. So this is it, where you can see that the blast furnace basically consumes in a steel plant 35 to 40% of total energy, whatever is being consumed in the steel plant. And since the majority of it is used for driving the turbo blowers, and almost 1/3 to 45% of the power which we give in the blower, we extract in the well-designed TRT system. So this is just a typical case for a 3,005 meter cube blast furnace. In this, our blowers are consuming in a range of 40 to 45 megawatt power, and here a well-designed system can give me back the power to the tune of 20 to 22 megawatt, thereby reducing the overall of energy consumption in blast furnace itself. Here, this is the simple formula which we all have learned in our engineering, just adiabatic expansion of the blast furnace gas. That means we are still retaining its calorific value. We are not doing anything to the blast furnace. We are only utilizing its pressure energy, and at the exit of the TRT, whatever gas is available, that gas will be further distributed in the steel plant for combustion purpose. So only its pressure energy is used in TRT, and we are extracting power. So very simple setup. You can see here, the right side is my TRT, and there we are having its generator. In another picture, you can see the cross section of TRT. It's a simple. We are just giving blast furnace gas from one point, and then since the volume is huge, the size of this typical turbine is huge. Means it is I'm talking about a length of 8 to 9 meters and a dia of approximately 3 to 4 meters. That is the size we are talking about. And in this, we can see that to extract the pressure energy, we are having adjustable blades, rotor blades and adjustable stator blades to take care of fluctuation in the blast furnace gas volume. And rest of the part are the integral part of a turbine, means the thrust bearing, journal bearing, and other things. So it's a TRT rotor, the actual picture which is there in a steel plant. And it's a typical layout, means you just have to route the blast furnace gas. The dia will be definitely high, means a 2 meter dia will be required to route that blast furnace gas from a gas killing plant, and then it will go to the TRT and give me and extract. We can extract power from it. It's a typical case of TRT supplied by Kawasaki, where we are having 20 megawatt of rated output power. So it's a simple flow diagram, means from blast furnace gas through GCP, then we are taking blast input from that gas header, and through inlet valve we are giving it to the TRT. There are flow control valves as well as bypass valves to take care of all pressure fluctuations. And even this bypass valve is very much required, because maybe if there is something happens in the TRT system, means there are rotary parts in the TRT as well as in the generator, and if due to some reason my TRT trips, but we have to continue with the blast furnace, then initially that pressure is being taken care in the pressure control valve, and then slowly and gradually we have to design our GCP system, that means those Venturi scrubbers, in such a manner that we can further reduce the pressure in the GCP itself. So during the period when my TRT is not running, or due to some reason or other, the pressure will be reduced in the GCP itself, and the desired pressure of blast furnace gas header, distribution header, will be maintained. So we are having two types of TRT systems. Mainly two types of TRT systems are basically because of the different type of systems we use for gas cleaning. That means the blast furnace gas, which is having huge amount of dust, means 2 to 4 grams of per annum cube of dust is there in the blast furnace gas, and we have to clean it to the level of 50 milligram per annum cube of blast furnace gas level. So to clean this,
please conclude.
Definitely, sir. Just 2 minutes more. So we are having either wet TRT or dry type of TRT systems, and wet GCP or wet or dry GCP. So it's a typical TRT performance curve. So instead of going to this slide, let me just go through this slide. This is the approximate different type of blast furnaces which are available in India, and we can see here that in more or less all the blast furnaces which is having a useful volume of 2500 or more, we have installed. The rest of the blast furnaces, either they will be phased out soon, or we will be installing TRT in the blast furnaces. For example, for SAIL, we are having 3 proposals for installing TRT very soon. So this is the conclusion. I have already covered that since steel making is very energy intensive process, and TRT is basically reducing the power being consumed in the iron making process. That means this TRT is now slowly and gradually becoming integral part of iron making systems. Thank you.
Thank you, Mr. Anand. Any questions? Any questions?
I have a question for Anand.
Yeah.
Yes.
Anand, you are talking about this dry type of dust collection system. Are there
Yes,
any limitations with respect to capacity when you are using dry type? Because I don't think in India anybody has installed this.
Sir, you are very right, sir. You are very right. In India, we do not have dry type of GCP yet, and we are not having dry type of TRTs, but definitely with dry type of TRT, when my gas is available at a slightly higher temperature, our energy potential increases by 2 to 3%. Means if we use in the same vis-a-vis wet type of TRT system, the energy being recovered in the dry type of TRT will be at least 5% more.
Okay, that is one.
Maitra sir, there is a big blast furnace working in second blast furnace of JSW Dolvi. They have installed a dry GCP and it is running well. It is one of the largest blast furnace, 5400. Okay. So large blast furnace also having dry GCP, and you are already aware many blast furnaces are all having many of the Chinese furnaces are having dry GCP.
Okay, sir. One more thing, sir. How much will be the pressure drop when compared to wet with the dry type of GCP? What is the pressure advantage we are going to get? One is the temperature will be more. At the same time, how much will be the pressure drop while you are installing a dry type of GCP?
No, pressure drops are in the GCP or in the TRT?
No, I am talking about in the GCP, because basically we are converting pressure into energy.
Yes.
So I think in our case, I think it is 2.5, roughly 2 to 2.5. That's you already told. I am talking about, sir has just told, Kumar sir will बताया they are operating a 5,000 meter cube. So what is the pressure, the inlet of the TRT?
Sir, as far as I am concerned, I do not have much exposure in GCP systems, but as for design purpose, we normally take 0.3 kg per centimeter square pressure drop in the GCP systems, whether it's a wet or it's a dry.
Okay. And And one more thing, sir. At BSP, we have installed this 14 megawatt. Just now, you were told that even with the 3500 meter cube also, you can go for 22 megawatt. So these are the latest developments, or deliberately we have gone for a conservative take?
Sir, I think in Bhilai we have got potential to generate more power, because if you can see in the ISP, we are having same type of blast furnace, same volume, and there also MES has supplied this TRT, and earlier it was limited for a power generation of 14 to 16, but now in that software interlock they have removed, and it has got potential to generate up to 20 megawatt. So definitely going forward in future, we will have the potential to generate at least 16 to 18 megawatt in the same furnace. I'm sure for this.
Okay, thank you.
Thank you.
Any other question? Yeah, no, thank you, Mr. Anand.
Thank you, sir. I'll just take leave because I'm having a meeting scheduled at Rourkela.
Thank you so much. Thank you. We will go ahead with the paper exploring the potential role of hydrogen in the Indian steel sector. Mr. Girish Sethi and Ms. Shruti Dayal, you are here?
Yes, yes, sir. Yes, Mr. Kumar. Can you hear me? This is Girish Sethi.
Yeah,
Okay.
you can please start your presentation, sir.
Thank you. Thank you. I'll just share my screen. Is it visible now, Mr. Kumar, my screen?
No, not yet come, sir.
Just a minute. Give me a minute.
Yeah, no, you are restarting. Yes, sir. Screen, it is visible now.
Yeah. The screen is yes, sir. It is.
Hello.
Yeah, it is visible, sir. You please start.
Visible now. Yeah, I think there was some issue. Thanks. Sorry for this inconvenience. Let me just start first of all by thanking, I think, the organizers. This topic, Mr. Kumar, is a bit futuristic topic, and I think definitely is of interest to the Indian steel industry. So that's why we just thought it is more of analytical and less of a technical presentation. So I'll just go ahead with my presentation, giving a bit of the background that why we are really talking about a different fuel, a technology which has been proven for hundreds of years, I think ever since steel is being made through the coking coal route, and why we are talking about hydrogen as a option for the steel sector. So we all know of the Paris Accord and the implications related to climate change. So many of the countries around the world have already committed to becoming carbon neutral or net zero in another 40 to 50 years. And it was at the Glasgow COP in November last year that the Prime Minister of India also made this commitment that India will be net zero by 2070, which is close to around 50 years from now. But I think, as we know, that heavy industry sectors like steel, cement are large emitters of carbon dioxide GHG emissions. So if we have to achieve this net zero emission in another 40 to 50 years, action will have to be made, because new plants, new setups have a lifetime of 30 to 40, 50 years. And if we go ahead with our conventional technologies, then we would be left with the old technology and will not be able to meet our international commitments in this regard. So the world is moving in that direction. So that's how this whole idea of how Terry started working on looking at the potential role of hydrogen in the Indian steel industry. So this was just a bit of a background, and I'll just go ahead quickly try to finish off in the 8 to 10 minutes my presentation. if you look at this slide, we started working with the steel sector, I think around 3 years back, more closely with the hydrogen as a focus. And we came out with this report, which is at the top left, which is called the Towards a Low Carbon Steel Sector. It is available on TERI's website. Anybody can download that. It is a detailed analysis of how one can move forward towards a low carbon sector. That was around 2 years back that we came out with this detailed analysis. Then subsequently, we also worked on efficient technology options for direct reduction in sponge iron industry, because we know sponge iron is one of the largest segments in India. And then subsequently, a couple of other more specific activities around hydrogen. And the last one, which you see on the right side, is this potential role of hydrogen. It's more of a broader role of hydrogen in India at economy level. And if one looks at this work on the role of hydrogen, if you look at this slide, which I'm projecting now, we have tried to see what role can hydrogen play in the industry sector in India as a whole in the next 30 years. We know that presently hydrogen is used primarily in India in the manufacture of ammonia through the Haber-Bosch process, and secondly in the refinery sector. So the total demand for hydrogen presently in India is around 5 to 6 million tons, around 6 million tons of hydrogen. And based on our analytical work and various assumptions and projections, so we believe that this demand for the industry sector would probably reach somewhere around 22 to 25 million tons by 2050. And the one which you see on the top, which is the blue color, the bright blue color, that is actually the demand from the steel sector, which we have considered if we were to move towards hydrogen-based DRI route, which is being talked about quite a lot in the European context and other parts of the world. So if one actually sees this, the maximum demand for hydrogen, increase in the demand would actually come from the steel sector, whereas the other sectors like the refineries and ammonia would be growing at a natural pace, because presently they produce hydrogen using the steam methane reforming with natural gas as a starting point, but they can also convert to the green hydrogen route. Now, let me just also mention that here we are talking about the production of hydrogen, only the green hydrogen, basically coming from the renewable energy sources. That is from the electrolysis of water. You produce hydrogen, and that hydrogen can then be used in the various applications. The other demand from our hydrogen, which is expected to come, is from the long distance heavy duty transport segment, which I have not covered in this slide, but that would be again a significant demand moving forward. And again, the third major chunk, which we refer to as the harder to abate sectors globally, is the demand for hydrogen in the shipping industry, the international maritime shipping. There again, I think ammonia is being talked about as one of the options. So this is just a bit of the background at why and hydrogen and how in steel. Now I'll just move to the steel sector very quickly. I think I don't need to spend too much time on these things, since everybody is from the steel sector and they know this. So it's essential for the development of the economy. But I think the point here to note is that the demand is going to increase. In the graph which you see on the left-hand side, India is way at the bottom. But if you look at the right side, these are the cluster of West European countries where steel use has started to saturate. So the steel use in the country is going to only increase in the coming decades, and that has been very clearly mentioned also in the Indian steel policy, which was referred to also by one of the earlier speakers. So in terms of the demand projections, which we at TERI have done it, we believe that I think steel demand definitely is going to grow tremendously. And even if we use the resource efficiency kind of options, like things like increasing lifetime of the buildings, increasing lifetime of the equipment, so that the demand optimization happens. Or even if we talk about the changing modes of working, maybe people preferring less of personalized vehicle and moving towards more ride sharing mechanisms like the Ola and the Uber, so the demand from the automobile sector comes down. Or because one of the largest users of steel is in the building and the construction sector, and COVID has taught us working from home. So things like that are very common. So maybe the demand optimizes in the years to come. But even if all those resource efficiency measures come up, still we will see almost 3 to 4 times increase in the demand in the next 30 years or so for steel, because the country is going to grow. And this slide basically shows the environmental and the economic externalities, the implications for it. And the importance of the iron and steel sector, if you really see, it's almost the total consumption of energy in the steel sector as a percentage of the total consumption in the industry sector. It's almost 1/4. So it's huge consumption in terms of the industrial sector consumption as a whole. So if steel sector has to reduce, if the industry sector has to reduce its consumption, steel sector will have to reduce its consumption and emissions. This is basically what we wanted to convey here. Now, in terms of the transition options, I think the bottom one, which is the CCUS route, has been very briefly talked about, I think, by the earlier speaker from Tata Steel, I think Ms. Rajita, where she talked about the Hisarna technology, which Tata Steel has been trying out in Netherlands, and they want to bring it to India. But that's the one which will actually utilize carbon capture, CO2 capture, use and storage. And I think there were a couple of questions in the chat box also on CCUS. So that's again a big challenge. It adds to the cost. The other route which is being internationally talked about is using the hydrogen DRI route. And what we are trying to convey through this slide is that if India has to move really towards a net zero by another 40 to 50 years, we will actually have to move towards having natural gas DRI processes initially, and then slowly blending low carbon hydrogen or zero carbon hydrogen into it. And then finally by 2040 or 2050, when we are, or 2040s, when we are able to have hydrogen at a fairly cheaper rate or at a competitive price, then we can move towards almost 100%, 90% use of hydrogen, which is coming from the low carbon sources. So the top one is basically we're talking about in the current decade, it should be slowly moving towards a natural gas or a syngas direct reduction route, moving towards blending of hydrogen, and then finally moving towards a full-fledged hydrogen production, which would be an easier process. We do all have in India, I think, 4 or 5 plants which are based on the natural gas DRI. But of course, I think the challenge, of course, everybody knows, is the price and availability of natural gas. We have also done some techno-economic analysis. I think these are just broad numbers. We believe that at a price of around $2 to $3 per kg of hydrogen, the current cost of production of, we would be able to match the current cost of production from the BF route. Of course, this really depends upon the price of the coking coal, because in India, I think the first presenter also clearly mentioned that we are mainly dependent upon imported coking coal, and that is a price which is very variable. And more so, I think the price of natural gas, if we are comparing with it, that's again a price which is highly variable, and it depends upon the international prices of hydrogen, of natural gas, and more so now with the Ukraine-Russia crisis going on, we are seeing the prices going through the roof. So, but broadly, what we wanted to convey is that if we are able to produce hydrogen in the country at $2 to $3 per kg, it can actually start competing with the conventional routes of whether it is a natural gas-based DRI or the coking coal-based BF route. This is just a variation, the same thing which I mentioned earlier. But presently, as I mentioned in the last one, it is not competitive. But the one which you see, the shaded part at the top on each of these 4 graphs, is actually the range which we have tried to project for each of these routes, the blast furnace route or the natural gas route or the hydrogen route. But that is all dependent upon the variability in the input prices of the different fuels, whether it's coal or coking coal or natural gas. This is again the same thing in terms of presenting that how we can actually reduce the dependence on fossil fuel based steel production. The 2050 bar on the rightmost side, the light blue color, is showing the hydrogen DRI route production if it's possible. whereas one can see the reduction in the dark blue, which is the blast furnace route, as the new older blast furnaces retire. We have not assumed any forced retirement of any blast furnaces. As the furnaces retire, one has to probably start thinking in terms of moving towards the new technologies which are being talked about. The demand for hydrogen for the steel would be approximately 9 million tons. That's what we see. And so finally, I think just to wrap up my presentation, Mr. Kumar, I think the what would be the strategy for this? It need not be all or nothing. I think what we want to convey is that it has to be in 3 pillars. The very first thing is that we must continue working on our existing path of energy efficiency, resource efficiency, and material circularity, which must be pursued for all the plants. I think we did have a very good presentation on the circularity by Tata Steel. So, but the fact still remains that today we do have plants in the country which are not so efficient in terms of their energy consumption. There are options to reduce energy consumption in the existing steel plants as well. I think the previous presenter from Bhilai mentioned about the top pressure recovery turbine. So that itself is a very simple, clear example of where the opportunities lie in the existing steel plants. Circularity is definitely an option. The second pillar has to be that we must start thinking now of deep carbonization options. The 2 graphs which you see at the top and at the bottom, there's not much difference in the 2 graphs, but the only difference is if you can see the bottom line, blue line in the bottom graph, where we have said that if we can start using hydrogen from 2030 onwards, then we can reach very close to net zero by 2050 or 2060. Whereas if we wait and start thinking about hydrogen when the world becomes more efficient in using hydrogen, that is in 2040s, then we will definitely be far behind as a country in terms of using hydrogen as an option. So this is basically trying to convey that the second pillar has to be a deep carbonization option with hydrogen as a hydrogen-based DRI route. And of course, if one can use the Hisarna technology, surely I think that would be an add-on, because that is kind of owned and managed by an indigenous Indian company, and that's the big advantage which we have. But again, I think the challenge there remains on the carbon capture and storage options or utilization, where we can actually utilize the CO2 which is emitted from that. And finally, I think what I wanted to convey is that in this area, because we are talking about new technologies, international collaboration and innovation is very important. One, of course, is collaborating internationally with Europeans. We know of the Swedish project, the hybrid project in Sweden, which is going on. In Germany with the clear leaders in the steel sector. But also, I think equally important will be a domestic plan or domestic policy by major players in the steel industry, like SAIL, and I think the Ministry of Steel will have to play a major role in pushing forward this whole agenda for a domestic plan to move towards cleaner technologies. And I think an equally important area would be to create the demand for this low carbon steel. If we really want, it cannot be a one-sided supply side option. It has to be a demand for the green steel will have to come in. So the major players, whether these are greenhousing projects in the building sector or public procurement by government for major infrastructure projects, or it could be the automobile sector who can take the lead in demanding low carbon steel. So these are the key messages, basically, I think, which I have basically talked about. I would think that if India is able to move in that direction, basically we would perhaps be one of the first countries or the first major economies to industrialize without the need to carbonize, because most of the other countries have carbonized and now they're talking about decarbonization. But in a country like India, which is yet to fully expand its industrial footprint, we can become a major player in terms of decarbonizing and at the same time growing at a fast pace. So thanks a lot once again for having me for this session.
Thank you, Girish sir. Thank you so much. Is there any questions from audience? Sir, you have mentioned in your presentation the reduction of blast furnace route of iron making. So, what is your expectation, sir? How many, how much blast furnace route it needs to be there, because that is the advantage. Large capacity additions can be done through blast furnace route only. What is your view on that, sir?
Yes, I know. I think the Indian steel, national steel policy also really talks about it. And I think that's the need for the country, which is growing at a fast pace of 8 to 10%. We definitely need that. But I think if we were to actually commit to this net zero pathway, the steel sector will slowly have to think in that direction. Otherwise, we would not be able to meet the net zero commitments. I know that's the biggest challenge for the steel sector. And I think the two biggest sectors in India which are going to face this challenge will be the steel sector and the cement sector. And I would rather say that the cement sector is far more challenging than the steel sector, mainly because at least here we are talking about a hydrogen-based process or a CCS technology. But where in the cement sector, I think there's very less research or demonstration going on, even in other parts of the world. Except for CCUS as an option. So surely this is a challenge, but I think my view or our view remains that the sector will have to start thinking in these lines now. If we can't do pilots in 2020s, then we will be left behind.
Yes, sir. Better late than never. Huh? I think that is good, sir. Thank you so much, sir. Is there any other?
MR, I have got one question to Mr. Sethi. It was really a nice presentation, and hydrogen is our future of steel making. Have you done any exercise of impact of hydrogen in cost making of steel per ton? What will be because this will decide. It's a very competitive market. So how much it will come? Have you done any exercise on that?
Yes, sir. I think we have done. I had one slide, but I just quickly moved on to that. But see, as I mentioned in my talk, I think the price point will really depend upon the competing options. So today for the steel sector, it is either the coking coal route or the natural gas-based DRI. There are just 4 or 5 plants in the country. So one will have to compare that with these two options. Of course, we have the sponge iron non-coking coal route as well. But I'm, for the time being, presuming that when we are talking about large plants, basically we are looking at the blast furnace option to be replaced. So it will all depend upon the landed price of natural gas or the landed price of coking coal, which we have ultimately. So in our analysis, as I mentioned, I think we believe that if the hydrogen can be made available at $2 per kg or less than $2, it can start competing with the existing options. And many of the large players in India, primarily I can name it, I think, like for example, last year, Reliance in its annual general meeting announced that they would be aiming to produce hydrogen at $1 in a decade per kg, whereas in our analysis talks about $2. So I would presume that $1, if it is at the production site, we add the storage and transportation, because hydrogen is a very difficult fuel to handle. That would additionally add some cost. So it can definitely be a competitive with the existing fuel in another 8 to 10 years, I think. But I think given the fact that the steel plants have a long gestation period, you need to take time to set up. So some initial pilots will have to start now, and maybe with large players like SAIL and Tata Steel will have to, or Jindals will have to take the first plunge in these things. That was just a thought. Thank you.
Okay, thank you so much, sir. Thank you, sir. Now we'll take a paper from ISP Banpur. The paper is on improving process efficiency and equipment reliability in coke oven byproduct plant. I request Mr. Sushant Kumar. You are here? Mr. Sushant.
Yes, sir. Am I audible, sir?
Yes, yes, yes. Please start. Please start.
Is my screen visible, sir?
Is not yet come, but it is showing like you are starting screen sharing. Double click to enter full screen mode. Screen is not visible.
Sir, I have shared my screen, sir.
Mr. Kumar, you stop sharing once and try to do it again.
Okay, ma'am. Ma'am, can I have shared it, but it's not coming. Can I share my PPT on your mail ID and you can project it on you can share your screen and I can just connect
yes,
to audio.
that can be done, but before that I am requesting you to stop sharing once. If you
I'm trying that. Stop sharing it. I have clicked on stop share. Let's see how much time it takes.
I think there is a network delay there.
Clicked on stop share, but
Parna ma'am. Hello. 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 Hello, ma'am. Hello.
You are audible, Mr. Kumar. You are audible to me.
Okay.
You are audible. Yes. You are audible to
Ma'am,
me.
I think we should. Ma'am. Sir. Ma'am, I should. We can go to next paper by that time. We can save some time.
Okay. So in that case, we can request Dr. Behra to present his paper.
Yeah. Yeah, we will go again back from for the taking paper from ISP Banpur. Now I request Dr. Pravas Ranjan Behra Saab to kindly please present paper on a sustainable technology to produce green and clean steel by hydrogen plasma smelting reduction. Please go ahead. Please go ahead.
Yes, is my screen visible to everyone? And
am
I audible?
Yeah, it is visible.
And is it visible in the full screen mode?
Yeah.
Great. Well, thank you, and I also thank Indian Institute of Engineers India for giving me that opportunity. Well, am I audible, right? Okay,
yes,
great.
Yes.
Okay. Actually, I wanted to be the last in the list to present, so that I could have got all that attention, but it's fine, no worries. So straight away to the topic. So the topic is like a sustainable technology to produce green and clean steel by hydrogen plasma smelting reduction. In short, we call that HPSR process. And so I'll go to the next slide. Okay, during the course of my presentation, I'll be touching upon these aspects, like what prompted us to choose this area, of research, and why we did that, and how we achieved that, how we ended up accomplishing that objective, and the trial that we have done in 10 kg scale, right from the start. We started from the lab scale, and then we optimized those experimental and process parameters, and then you attain that success in 10 kg scale, and how the things look very bright to immediately go for the pilot scale, like to test this process in 100 kg scale. And if time permits, I'll be also sharing some video clips with you. Okay. So to have a quick, look, of course, as apparent as it is, iron and steel industry, like it is the backbone of India's economy, and it represents almost 95% of all metals used per year. And all over the world, the current crude steel production is around 1869.9 million tons, and also like everyone is aware that India is placed second, in the world in terms of crude steel production, only next to China. But again, we should not forget to embrace the fact that China controls more than half of the world's crude steel production. So it will take some time for us to catch up with China. And this is how the annual crude steel production has grown over the years. Like it has grown by leaps and bounds. Like if we compare the 2019 production figures to 2012, like it has reached a historic high. And like I have already said, like how means the percentage of crude steel contributors in the entire world, and India is at the second position in the world. Okay, and okay, the immediate concern is that these global energy related CO2 emissions, like the greenhouse gases emissions, they have grown by 1.4% in 2017, reaching again a historic high of 32.5 gigatons. And if we talk about India alone, we can clearly see, we can clearly observe that our over dependence on coal as a as a major fuel source. So here, we must not forget that, to produce 1 ton of steel, we're generating almost 2.5 times of greenhouse gases to the atmosphere, to the environment. So and India at the same time, India aims to touch around 300 million tons of steel production figure at the end of by 2030. So if you see that it will release more than 600 million tons of greenhouse gases to the atmosphere, so that is quite alarming. So the production of steel is not going to stop, and everyone knows that. So what we can do is that the production of steel continues, but we can curb that that the pollution we cause to the environment, like from the steel industry. And at the same time, India also faces the temperature rise concerns, and it was it was covered in BBC News. And recently, yes, recently it was kind of published in MOE's Ministry of Earth Sciences that temperatures in India could rise by 4.4 degrees Celsius by 2100, it means by end of this century. And the receiving end in India will be New Delhi, Delhi is going through a very lean period when it comes to the clean environment. And so why we kind of chose to go ahead with hydrogen plasma. So of course, with production of iron, iron and steel industry, they are one of the major contributors to greenhouse gases, and the only way to get rid of these to come up with a green fuel, and hydrogen is the future energy, and hydrogen is here to stay. Just that the only hiccup, means it was already covered that means we are not ready yet to get hydrogen from natural resources, like from maybe H2O or some gases, and means we are not ready yet to support that to like in industry scale. But they are the researchers, they are trying hard, like in the entire world, to come up with a sustainable technology to get hydrogen from natural resources. And once that output is established, which is ready to support the industry scale, then this hydrogen is it looks promising to be used as a reductant in iron and steel industry. Well, and in case of this hydrogen plasma smelting reduction, the only after smelting reduction, the only byproduct that comes out of this process is H2O, and like of course it is in the vapor form, and which can be condensed back into water, and it can be again recirculated in the circuit. Okay. And interestingly, this is the fact and figure, like to produce 112 tons of iron, we are consuming 36 tons of carbon as a reductant. Like we are using carbon as a reductant, and in turn, it generates 84 tons of CO, carbon monoxide, to the environment, along with 16 tons of CO2, carbon dioxide, to the environment as well. But over here, if you compare with hydrogen as a reductant, to produce the same quantity of 112 tons of steel iron, we are consuming just, we require just 6 tons of hydrogen, as compared to, like it is 6 times lesser as compared to carbon. And forget CO2, we are just ending, like means we end up just generating 50 tons of H2O, like which can which could be again recirculated in the circuit. And also over here in the typical iron making and steel making process, like we have to depend on number of unit operations, like from ore, then DRI, then again we use that LD converter to make steel. Then again, if there's phosphorus, we have to do dephosphorylation, then like to get rid of sulfur, desulfurization. Again, if there's high carbon, we have to also go through decarburation process. But over here, in this case of hydrogen plasma spectral reduction, it is a single step process. You directly use the ore, you directly feed the ore, and also you can feed in the form of fines. So this route also like shows a possibility, like you can use iron fines. So over here directly you put fines, you feed fines, and it goes to instant smelting, like through hydrogen and in plasma environment, and you end up getting the steel. And over here, like if you see the hydrogen as a reductant in its molecular form, it is a mild reductant which is placed very close to this Usted reduction. And when it is thrown into the plasma environment, this molecular hydrogen breaks to atomic hydrogen, which is 3 times reactive than that of the molecular hydrogen. And as it continues in the plasma environment at means at 1800 degrees Celsius, it again kind of breaks down to ionic hydrogen. So this ionic hydrogen is 15 times more reactive than the molecular hydrogen. And if you see where it is placed, so it can reduce all oxides in the system. So this is the game changer why we chose to go ahead with plasma. And also like the fact, like above 1500 Celsius, the liquid oxide ion phase attains the equilibrium, and the ratio is which is like 60% hydrogen and 40% H2O, and it stays as such up to 2400 Celsius. So and this is why this hydrogen plasma environment it is kind of very suitable for us. And this is how the gas oxide surface reaction model Ajeet is highlighted over here. This is how the reaction proceeds. Like the hydrogen removes, like takes away that oxygen, and it is left with iron. And as a specific gravity of iron is high, so it gradually settles down, and the slag is slag floats at the top. Go to the next slide. Okay, this is the entire journey that we had planned, and we had attained our objectives. The whole objective was to produce steel having very negligible amount of carbon. And we initially we started with of course I'll be focusing on this. It was we started with arc plasma, but again we got some carbon into the metals. Then we switched to microwave hydrogen plasma again, it was kind of DRI kind of thing. Then we did microwave hydrogen plasma reactor again, it was kind of free from carbon, but again we ended up producing DRI, and these are non-thermal plasma or cold plasma, like you say. And then it switched to thermal plasma. So here
I'll say next, and then you can keep
yes. So we slowly started really realizing our objective in this thermal plasma smelting reduction. And from like we started from 200 gram scale, then optimize this experimental parameters, then we gradually scale it up to 400, 600, then 800, then okay. So over here I'll talk about hydrogen plasma smelting reduction, and it was not that easy as it seems to be. We made several attempts to finally arrive at a polished reactor setup, and the first attempt, second attempt, they had some like hurdles. So at the fifth attempt, like we could arrive at this refined setup. So this is a typical hydrogen plasma smelting reactor, and it is housed in CSR MMT. And we have a plasma touch over here, like it is an electrode, of course, and it has a water coupled crucible. So there is a charge difference, and we maintain.
Dr. Behra, please conclude.
Yeah. So I'll just so the raw material we started from iron ore, like we also utilized the lab grade, and we also got that from got the raw material from industry as well, and this is the entire process in in a nutshell, the flow sheet. Like it is it is a single step process. We just use iron ore fines, and we just make some granules out of that, and the final product is rich in iron, which is around 99.5%, and the phosphorus sulfur carbon are very low, and you don't need to have those unit operations like dephosphorylation, desulfurization, decarbonization in place. So that saves a significant amount of cost. And so this is how started with 200 gram scale. Then we analyzed all those and we optimized those parameters. Then you scaled it up to 200. I mean, as you observed, like as you scaled up, the recovery, the percentage recovery increased as well. And we went to 800 degrees Celsius. Then these are like we did more than 19 number of experiments, and this is the scale like in 1 kg scale like we did, and these are some good and consistent results that we we got, and we studied the effect of time as well, and we optimized the time around 100 minutes, and this is the effect of hydrogen fluoride. We wanted to see the volume of hydrogen, how it plays the role, and we also kind of optimize that. And this is one example of a typical failure experiment. Like as you can see, this is the metal phase, and some metal droplets that trapped in the slag. So as the reduction happens completion, they gradually get released to the bottom. And these are the effect of hydrogen fluoride, or the effect of volume of hydrogen. How 800 liters of hydrogen is showing prominence, like how the metal layers are visible. And also like when the hydrogen is further increased to 1200 degrees Celsius, the metal layer and the slag layer, they are kind of very distinct in terms of appearance. So yeah, means I will done in next 2 minutes. Yeah. So after successfully optimizing those experimental parameters in 1 kg scale, we immediately emulated that. We replicated that in 10 kg scale, utilizing the facility of MS Tata International, which sits at the industry belt Haruch in Gujarat. We went over there. So we successfully did that, and this is there is no time to play the video, so it's fine. So and this is the product that we got in 10 kg scale, that the well scale we say, and this is the pure metal as it is evident from the XRT. And recently the Cell R&D team visited, and they have shown interest to join hands with to scale it up to 100 kg scale. And this is the typical comparison of hydrogen plasma reduction process in with the traditional process and the new one. And we could see that 21% of energy consumption, like we are bringing down around 21% of energy consumption. And as it is shown over here, so like the R&D of this process is at its grooming stage. It is at its nascent stage. So as the R&D kind of achieves success, so this gap will be gradually narrowed down. And so these are the takeaways of this process: reduction in energy consumption, reduction in specific raw material consumption. Means we don't use several raw materials, just kind of the hydrogen and the iron fines, that is enough. And the product quality is significantly superior as compared to others, and it it has a provision of direct use of iron ore fines and reduction in emissions, of course, and utilization of Western byproducts can also be explored through this FPSR process. And this is how we have, we intend to go with the 100 kg scale. We have submitted the proposal to the Ministry of Steel and also to CSIR. So hopefully, it will see the light of the day very soon. And the videos wouldn't have time. So thank you for your kind attention. If there are any queries or questions, you're welcome.
Yeah. Thank you, Dr. Behra. And if anybody has a question on this, yeah, thank you. We will ask Mr. Sushant. Are you there?
Yes, sir. I'm there, sir.
Please share. You will have to conclude within 10 minutes. You have already used previously 3-4 minutes.
Go to the first slide, madam.
Yeah. Start.
Slide. Yeah, let bring to the first slide.
Yes, it is
visible. Please go ahead. It is visible. Please go ahead.
This is the second slide. Okay.
No.
Bring to the first slide. This is the second slide.
I have shared already, sir. Please go ahead.
Okay. Please open the first slide, madam.
Sir, this one is
Sushant,
the first slide.
Please go ahead. We know the title of the paper. Your paper we know. You please go ahead.
Okay. Next slide. I'm here to present on the topic improving process efficiency and equipment reliability in coke oven byproduct plant. Next slide, please.
A slide has been changed.
Okay, which is not visible. Okay.
You are facing a network issue at your end, but other participants can see this.
This is the flow of my presentation, wherein I will be discussing about the steel industry byproducts. Then I'll be talking about the coke oven byproducts, and then finally I'll be talking about the improving coke oven byproduct process efficiency. Next slide, please. This is the process of the steel industry, wherein we make coke and then we go to the blast furnace. We go to the blast furnace. We go to the blast furnace, wherein we have all stages in steel process generates byproduct.
The slides are not moving. We can't see the slides.
Yeah, slides are not moving. Even I am not able to see. Madam is sharing actually.
Okay.
Madam from is sharing. I have sent my slides on mail.
Yeah. It is visible now. You please.
MR has
Yeah, now it has
come. Can you hear me now?
Yes, now it has come. Thank you.
Yeah. Please.
Okay, sir.
Ma'am, go to next slide.
Yeah, these are the coke oven byproducts like coal tar, elemental sulfur, ammonium sulphate, and naphthalene. Next slide, please. So this is the flow diagram by which we produce byproducts and clean the coke oven gas. First, the coke oven gas generated from battery comes to the downcomer, where the tar gets separated and is sent to the tar separation plant. Next, the gas needs to be cooled from 80 degrees Celsius to 20 degrees Celsius. So it is sent to primary gas cooler, that is the PGC. Next, we sent it to electrostatic tar precipitator to remove tar particles in it. And then the gas exhauster is placed. Hello.
Yeah.
Yes, sir.
The purpose of which is to suck gas from coke oven battery and send it to customer departments. The next in the next stage, the gas goes to the scrubber units. So these are the major units. Next slide, please. Next slide. These are the major units of a byproduct plant: tar separation plant, primary gas cooler, electrostatic tar precipitator, gas exhauster, ammonium sulphate plant, stripper deacidifier plant, and the sulfur plant. In the coming slides, we'll be discussing how to improve these efficiencies. Next slide, please. These are the major equipments consisting of gas exhausters, scrubbers, deacidifiers, strippers, and saturators, and catalytic oven reactor and the closed reactor in a byproduct plant. Next slide, please. So first is the tar separation plant. This plant is supposed to remove tar from coke oven gas and separate liquor or the condensates. So this is the solid decanter on the right side, you can see. So in this conveyor, what we have done is we have installed rubber liners on the conveyors to improve the efficiency of removal of sludge from liquor and tar. So sludge is an enemy in byproduct plant which chokes the pipelines and the nozzles. So for improving the efficiency, we have used rubber liners, and also it improves equipment life, acting as a flexible member. Next slide, please. Next slide, madam. Yeah, this is the tar storage tank. Again, in this, what we have done is we have made a new recirculation line. What it does is when the sludge comes in the line, when we are supplying it to the customers, the sludge needs to be drained out on the roads. So what we have made is a new recirculation line we have made into the tank, which can recirculate the sludge particles to the tank again, and then when the pure tar starts coming, we can supply it to the customers. And also we have changed the position previously. Yeah, we have changed the position of the pump so that the sludge particle doesn't go to our customers. And you can see we have removed the refractory over here. What we do is first time we have done it in steel industry in sale, that we have cut this tank and we cleaned this tank using a JCB to remove sludge particles. Next slide, please. This is the electrostatic tar precipitator. It is supposed to remove tar from the coke oven gas. It works on cathode anode principle, wherein the cathode negatively charged particles gets attracted to the tar and gets connected to the anode. So in this, the distance between cathode and anode are very small and needs to be cleaned regularly by flushing pipe to increase its efficiency. So the efficiency, the original nozzle which was provided to us was had a micro opening in it, which was getting clogged by the impurities in the liquor of the flushing liquor. So what we did is we modified the nozzle, as you can see at the top. We modified this nozzle so that this clogging effect is not there, which improved the efficiency of ETP greatly. Next slide, please. This is the ammonium sulphate plant, which is supposed to generate salt from the coke oven gas. Here the vapors from stripper deacidifier comes in the form of NS3 and H2SO4, and we react it. NS3H2S vapor comes in this saturator, as you can see in the figure. We react it with sulfuric acid, concentrated sulfuric acid, which produces salt. But as you can see, the media, which I am talking about, is highly corrosive, the ammonium sulfate vapors and the H2SO4s. So what we did is we made the internals of this saturator from Hastelloy pipes, which greatly improved its efficiency and the reliability and the performance of the saturator, and increased the yield of the salt on per month basis. Also, the pump supposed to pump these media or the liquor were getting heavily corroded. So
Sam, please go ahead. Please go ahead.
Next slide, please. Also, we monitor the this is the centrifuge internals, which is supposed to cut salt, remove salt from the liquor. So we changed the MOC of this to duplex stainless steel from SS316L. So it what used to happen is the salt particle used to go with the liquor. So by changing this MOC, these micro openings or the micro gaps between the centrifuge plates were maintained, and we didn't lose any salt, and it increased salt yield. Next slide, please. This is the most important equipment of the byproduct plant, that is the gas exhauster. So what we have done is the tar particles used to reduce the life of the rotor, which is highly expensive. So the condensate line supposed to remove tar condensates used to get choked. So we increased the diameter of the condensate line, as well as we gave new steaming points and the flushing liquor line on this to remove. Also, to improve reliability of exhauster, we made a new water line to it to maintain the bearing temperature or the hydraulic oil temperature of the exhauster. Next slide, please. This is the distillation plant or stripper deacidifier plant. This plant receives liquor, extra flushing liquor, and treats it before it is sent to BOD plant. So the heat exchanger.
Please conclude. Sushant, please conclude.
heat exchangers in this plant are get choked by sludge. So we incorporated an online cleaning system to heat exchanger. Also, we made an strainer, adopted a strainer in liquor line to remove sludge and tar. Next slide, please. This is the BOD plant. In this, surface aerators are used. In addition to this surface aerator, we gave new air lines to the liquor, which increased the microorganism or the bacteria growth in it, which reduced the cyanide content. Also, we changed the MOC from MS to SS, which reduced the weight of the plate and reduced the energy consumption of it and increased the efficiency. Next slide, please. So finally, concluding it, the purpose of these improvements are to increase the crude tar yield, which we have achieved as 4.5 ton per hour, to improve the ammonium sulphate yield, and to improve the naphthalene yield to 15 kg per hour. Also, we have maintained the coke oven gas, clean coke oven gas impurities as per norms. Tar 0.02 gram per normal meter cube, hydrogen sulfide 0.8 gram per normal meter cube. Thank you. Next.
Thank you, Mr. Sushant. I think, is there anybody having any question? Because this is very important paper which is done on the coke oven byproduct area. Is anybody having any question? Otherwise, we can conclude. Yeah, thank you. Chairman Saab, can you have your remarks?
Yes.
Sir.
Okay. So it was really very thought-provoking papers. All papers were really very good. To start with this paper from CMPDIL, Puspa Raj Verma. Can I conclude the papers now? So that next session will start, right? So Puspa Raj Verma has given a lot of in details about in indigenous use of coke.
Sir, Abha ma'am has given the paper. Abha ma'am.
Yes.
Yeah.
Mr. Abha Prasad, right? Okay, fine.
Yeah. Abha Prasad.
Yeah. See, just paper was very good. She has given also, but steel making and all that is very competitive, and we are heading towards very high-ended alloys and all that. So coke quality and all that, it matters. So washing of coal and all that has to be taken up very vigorously, and it has to be done very fast because our target is very high. By 2030, we have to compete. We have to meet 300 target. So already we are delayed, and I think all beneficiaries, they have to take very fast action on that. A second paper was for energy recovery through TRT by Mr. Trivedi. I think TRT is being used in all new blast furnace, and in upgradation also it will be used. It's really high energy recovery, but we have to think for heat recovery also, because he has indicated around 45% energy we are recovering through TRT. That's a huge value and very ambitious. So we have to think for heat recovery also. Paper was very good, and it is being implemented also. Third paper was by Tata Steel, Mr. Hussain, Circular Economy to Tech Resources. They have explained how much we can achieve. 40 lakh crore we can achieve by 2050. It's a very, very highly ambitious figure. 40 lakh crore, then we are sleeping. Or this figure has to be analyzed again. Everybody is struggling for carbon emission, fuel efficiency, waste utilization, for scrap and all that. Already in plant, 100% scrap utilization is there. Waste utilization we are working, and all new plants we are going for highly efficient energy recovery and heat recovery and all that. So if 50 lakh crore we are going to achieve by 2050, there should be more analytical and more detailed papers where we have to attack and where we are lagging. And it should be I think, spread very openly to everybody so that this can be achieved. And this will be in consonance with our Atmanirbhar Bharat also and waste utilization. It was really very impressive and very good paper. And fourth paper was for potential role of hydrogen in the steel sector by Mr. Sethi, that we have discussed in detail from TRI. See, hydrogen fuel is our future fuel. Everybody is trying for, because carbon emission has to reduce drastically. We don't have any option. That has to be reduced. But we have to see the economy, because foreign, we cannot compete with other developed countries. We have to see our resources and our demand. Still, we are lagging behind. And it is better if he can analyze what is the quantity of steel other countries are making through hydrogen based. Because a lot of problems are there, which has to be handled. Figures are very rosy, but a lot of work is required. And I think now people are serious. We hope in the near future, something more concrete will come. But this paper has given a very clear insight that, okay, $2 per kg is the value now. Target is to achieve 1 kg per dollar, and then will be competent. Then I think that will be better. Then fifth paper was by IMMT Bhubaneswar, plasma steel making. I think this, I have read their paper earlier also. They have completed their research. Now they have completed research, I think, quite early. Now they have to go for pilot plant, and this has to be implemented because it's really good. It is directly reduction of iron ore to steel. And it will give the dent in steel industry. But we are moving very slow. I don't know what problem is coming. This has to come up very fast. We cannot take 5 or 10 years in this progress. But he has given all the details. Paper was very interesting, thought-provoking. Good. Then last paper that from Burnpur, he has given all improvement what he has done in byproduct plant. See, he has explained very nicely. He has given all whatever he has done. But I'll only suggest that all plants are doing some improvement in their equipment and all that for better efficiency and all. But this has to be implemented in future plants, and this has to be informed to other plants also, of sale plants, so that first it has to be implemented in new upcoming plants. If they are changing MOC, then for new plants, this new MOC we should get. We should not face the same problem again and again. So somewhere we are lacking here. Everybody is doing some improvement at their end, and it ends there. In other plants, problems remain. So some work needs to be done so that this information goes to all the plant very fast, because we have to think for complete India. If we are protecting some information, then we are keeping our country behind. And same thing, you see what he has done now, same thing will come through foreign country after 5 years. This is happening. So we are doing improvement, but we are not taking advantage in all the plants. So our suggestion will be there that it should be implemented immediately, and it should be informed to all the plants. Okay, these are the improvement we have done. Others also should try and do it. So with this amending, but really papers are very nice and a lot of things to be done. Maybe we can discuss in detail, and things has to be taken forward again. Thank you.
Thank you, Chairman, sir. Ambassador Saab, it was very, you have concluded very nicely of each paper and the importance of those papers. I thank Ava ma'am, Mr. Anand Trivedi, Dr. Hashmi Jamal Hussain Saab, and Ms. Rajita, and Mr. Girish Sethi, Sushant Kumar, Pravas Ranjan Dehraji, and thank you all. And we will start immediately the next session. Aparna ma'am, are you taking over?
Thank you, sir. Thanks a
Thank
lot.
you, ma'am. Thank you. Thank you.
Thank you very much, session chair, sir, and the rapporteur, sir. We thank you for your nicely coordinating the session as well as nicely concluding the technical session 3. Thank you very much, all the panelists, for your time. We are directly moving to the technical session 4 of this national convention. I would request Mr. Ajeet Kumar, Chief General Manager, CET Cell. Sir, kindly switch on your video so that we can identify. Thank you, sir. And Mr. S.K. Das, CET Cell, who is the rapporteur of this session. On behalf of the Institution of Engineers India, I welcome Mr. Ajeet Kumar, Chief General Manager, CET Cell, Ranchi, and Mr. S.K. Das, CET Cell, who is the rapporteur of this session, and all the panelists who are going to present the paper. We are having 6 papers in this session. Couple of papers are, 3 papers are from Mekon, one from Bokaro Steel Plant Cell, and another one from RDCIS Cell, Ranchi, and so total 6 papers are there. I would request Chairman Sir to commence the session. Thank you, sir.
Hello, good morning.
Yes,
good morning, everybody.
Good morning, sir.
We are almost in time, so let's start immediately. We have got, I think, 80 minutes time is being given to me.
Sir, we have requested all the paper presenters to present for 12 minutes.
The 12 minutes time is not there, because what is the concluding time? 1:10 is given to me.
Yes, sir. 1:10 is the time. So at this moment, we don't have 12 minutes for each of the paper presenters. So we can minimize it up to 10.
10 minutes. So it should be 10 minutes. Presentation time will be 10 minutes for everybody. And we may have one question of 1 or 2 minutes question answer session. So to give you the paucity of time, we have to go like this. And I request my rapporteur to start the session and start with the people. Okay. So you come down from
Good morning. I now request Mr. Jayant Mandal and Mr. Kumud Ranjan to present their paper on sustainability of iron and steel industry, who are from Mekon. Mr. Mandal and Mr. Ranjan, please.
Good morning, sir. Am I audible to all of you?
Oh, yes, you are.
Does my screen share, sir?
No, not yet.
No, sir. Not yet. If you have already shared your screen, sir, I would request you to stop sharing once and then start again, because we cannot see anything on screen.
Just a second more. Is it visible now?
No, sir. We cannot even see that you are sharing anything. So, sir, I think there is some network issue at your end.
Yeah, might be, ma'am. Do you have my presentation, or can you share from your end?
No, sir, I don't have your presentation. So, are you clicking the green color share screen button?
Yeah.
but here it is not transmitting that you are sharing any file. Sir, in that case, you can mail your, yes, now it is coming. Yeah,
Now it is
has
coming,
come.
na?
Yes, sir.
Okay.
Please make it in presentation mode.
Okay. Good morning to all of you, sir. Today, my presentation is on the sustainability of iron and steel industries in Indian perspective. So what is sustainability? The Brundtland Commission defines sustainability as meeting the needs of the present without compromising the ability of future generation to meet their own needs. And it is not just talk about environmental, it is the combination of environment, economy, and society. These are the three pillars. And it is directly connected to the efficient and effective management of resources. Yeah. Now, when this all the three pillars of sustainability, that is people, economics, and planet meets together, a product, a process becomes sustainable. Now, from 2004, World Steel reporting sustainability based on 8 sustainability indicators. In last year, also 94 companies have contributed to this, which representing 53% of global crude steel production. From our country, JSW, RINL, SAIL, and Tata Steel have contributed to this factors. Now, it has 8 parameters, 4 from environment, 2 social, and 2 economic performance. Now, if we see, all the parameters are getting improved from the initial years, and few have improved a much better way. So, as we know that steel is 100% recyclable material. So, steel production are conducive to reuse and remanufacturing, which make it ideal to circular economy. In order to make it, our steel companies have to recycle much resources and waste generated in their plant as possible to make it happen. This is a pictorial of circular economy, how it is happening. Once steel is being produced, it is used, and after use, it is recycled and come back in the system again. And in turn, it reduces the raw material consumption, energy consumption, and all that. Now, what are the challenges to our industry and why it is important? Steel, as we know, it is accounts for 3.5% global GDP and creates around 46 million ton direct and indirect job. But at the same time, it is one of the largest consumer of energy and emitter of greenhouse gases, accounts roughly 7% of global GHG. So the cutting CO2 emission is indispensable at the need of the hour. Although the energy intensity has come down to almost half in last 4 decades, but absolute increase in production gives absolute rise in energy consumption and GHG emission. So with the present technologies, it is not possible to achieve the target. So we need to rely on measures like best available techniques, currently innovative technologies, carbon capture and storage, and green hydrogen steelmaking as far as possible. So our Indian steelmaker faces a lot of challenges. I will deal one by one in the upcoming slides. Recyclability is a big issue in our context. So recycling not only saves the raw material, it at the same time it reduces the consumption and reduces emissions. In India, the steel scrap recycling policy helps manufacturers to invest more and more on the scrap-based technology. So fully realizing steel recycling potential requires effective collection and infrastructure, as well as appropriate manufacturing processes through electric route only. Now, raw material. Raw material contributes 60 to 70% total cost of steel making. And we know that principal raw material are iron ore and coking coal. In India, we have fairly good reserve of iron ore, but the regulatory intervention, process efficiencies, and technology improvements related to ore extraction and its beneficiation are the challenges to the companies. So to ensure sustainable growth, judicious use of raw material is required for steady supply over a long period. And it is very much essential to utilize low and lean grades of iron ore, mines rejects, plant tailings by adopting proper beneficiation techniques. We know that while mining, around 68% iron ore comes out at fines and only 32% lumps. So this fines needs to be agglomerated in the form of pellets. Pellets not only increases the productivity, at the same time it reduces the coke consumption, in turn reduces the emissions. Pellets can also be used in sponge iron plant for DRI making. Now, while there is a gradual shift from conventional BF route to electric route, use of pellets are also like to increase substantially. Therefore, need to strengthen the beneficiation technology is very much essential. Although we have few limitations regarding other raw materials like high-grade manganese ore, coking coal, steel-grade limestone, etc. And India still imports more than 85% of its coking coal requirement, but its price fluctuation and availability makes hindrance to our blast furnace operator. We have to reuse the byproducts also to become sustainable. As we know, the steel products generates many byproducts, which are the inputs of other industries as raw material. For example, blast furnace slag are very common to cement industries for cement making. There should be zero discharge plan in place, which gradually reduce the water footprint. Hot flue gases are to be collected and cleaned before being used by the other consumer. Dust and slags are to be processed to recover other metals and its reuse. Shifting the production process is also very much the need of the hour. Now, BF route consumes generates lot of emission and consumes lot of energy. On the other hand, DREF route primarily relies on natural gas and electricity and uses DRI and scrap or their combination as the raw material for steel making. The present share in our country of oxygen and electric steel making are roughly 45 to 55%, and which is going to be widen more and more in the years to come, because the emission and energy intensity of DREF production routes are 1/3 or 1/5 less respectively than BF routes. Now, if we produce this steel through scrap-based steel making, it will reduce further. But the scrap availability in our country is a big issue. Steel companies are nowadays also experimenting with carbon capture and hydrogen injection to reduce or eliminate the emission. If these technologies are mature enough and can be applied successfully on large scale, they could prove to be a game changer to the industry. There are environmental issues also. The EAF route, the emissions are much less than the BF route. But the electric route steel making in our country mostly ranges between 0.5 million ton or smaller capacities. So these smaller steel plants not fully automated, neither they are environmental friendly intervention. Automation plays a very vital role in integrating the process efficiency to lead towards reduction as well as to become environmental friendly. Logistics is a big issue in our country. Unlike many developed countries, our plants are mostly in inlands and often in remote areas, which serves severe logistics challenges. We know that roughly 3 to 4 tons of raw material is needed for 1 ton of steel. So therefore, this much of logistic plays a significant role, and it has to travel through a network of ports, railways, and roads to reach the final destination. In our country, this raw material transportation is heavily reliant on railways. The high cost is resulting from the compulsion of our Indian railways to subsidize passenger carrying cost with freight earning. Now, the dedicated freight corridor, once completed, it will not only decongest our existing railways, but also help timely movement of cargoes. Ports also suffer very low productivity, slow unloading, and other bottlenecks, result in inefficiency in the system. As Niti already estimated that our steel makers are paying $20 to $25 more per ton of finished steel because of only logistics challenges. Power cost, over the last 4 decades, the energy consumption per ton of steel has already been reduced to 50%. Still, it is
sorry
very
to
high.
interrupt. Please, we have to be fast.
Yes, sir.
Almost 10 minutes. So please conclude.
A couple of minutes more.
Please conclude.
The cost of energy accounts 15 to 20% of the total steel production. So we have to reduce our specific energy consumption. The world-based figure is roughly about 5.4 gigacalorie, whereas in our case it is approximately more than 7 gigacalorie per ton. So we have a huge scope in reducing. Finance cost in our country is also very high. Although RBI reduces its repo rate from 6.5 to 4% now, but still Indian steelmakers have to face the challenges to their competitors from China, Japan, Korea. The share of bank credit also reduced for the iron and steel sector. And the finance cost also add up around 30 to 35 US$ per ton of steel. Now, if we see there, the bank credit for the steel sector is around 11% in the year 2011, which has reduced to 10%. Also, duties and taxes in our country is much more, amounting roughly 2,700 rupees per ton, and 40% of this contributed by iron ore itself in the forms of royalty, clean energy sales. So government need to intervene in this area as quickly as possible. Overall, we have a cost advantage of 80 to 100 US$ per ton, and which government need to ensure to remove this as soon as possible to make our steel companies to export more and to limit cheap imports and to become globally competitive. So where are the demand comes from? Mainly more than 65% of demands comes from the construction and infrastructure sector, and roughly 15% share by the capital goods and around 10% by automotive sector. Many government projects like Bharatmala, Sagarmala will gives the opportunities to the steel makers. The realty sector also boosted up by the affordable housing construction. The urbanization rate in India is around 33% now, which is expected to rise 2030.
Please close, sir. This time is up. Please conclude. I have to give time to others also. Please conclude.
In a big push in the infrastructure sector also catalyzed by the growth in the capital goods sector. The automotive mission plan also give a substantial demand for steel in the near to long term future. Now, government needs to intervene. Although large plants are implementing in green and cleaner technology, but MSME sector are lagging behind. So government need to intervene and significant incentives to be provided. SRTMI has already been formulated to promotion of R&D activities. Thus, recycling policy and steel product quality control orders are also few noteworthy steps by the government towards cleaner and greener steel industries. So in conclusion, I can say that the government steel industry is required to scale up new technologies, scrap-based steel making, judicious use of raw material, reuses of byproducts, and decarbonization pathways such as carbon capture and hydrogen, use of hydrogen wherever possible. And also, steel industries to be more sustainable continue to boost more on infrastructure, improve cost of finance, competitive tax structure, and government has already initiated few steps towards achieving this goal. Thank you, sir.
Okay, thank you for nice presentation, sir. Actually, we are running out of time, so we'll not be able to take questions. So we'll straightway move to the next presentation, please. Please, next presentation we should start. Who is that?
We'll conclude at the end of this session for all the presenters. But for the moment, I would like to invite Mr. Ajeet Kumar for his paper, Implementation of Industry 4.0 for Sustainability in the Indian Steel Sector. So, Mr. Ajeet Kumar, please.
Good afternoon, sir. Yeah, I'll be sharing my screen. Janta, sir, if you can unshare the screen.
Yeah, just a second. Yeah, I have done.
Okay, thank you. Is my screen visible?
Yes, your slide is visible.
Yeah, thank you. May I start, sir?
Please.
Yeah. Good afternoon to everybody. I am Ajeet Kumar, Senior Manager, Mecon Limited, and topic for today is a study of top 10 enablers for implementation of Industry 4.0 in Indian steel sector. Okay, now Industry 4.0, famously called as fourth industrial revolution, it was introduced for the first time during Hannover Messe in the year 2011 and was officially declared as a strategic initiative by Germans to revolutionize the manufacturing industry. The human-machine interaction is made possible through the connection between the physical world and the virtual world through Industry 4.0, which helps the different components and products to self-adapt and self-manage through a communication network for realization of smart factories. And the main aim for implementation of Industry 4.0 is to produce smart factories, which are ready for energy optimization, customization, flexibility in operation, and achieving overall efficiency through controlling, monitoring, real-time information processing, and self-optimizing. Now, objective of this paper and this study is to analyze the enablers for implementation of Industry 4.0 in steel sector in India. And I have used multi-decision criteria decision-making model through ISM, interpretive structure modeling, to understand the different relationship between these enablers and to model them through a hierarchical model to understand which enabler has to start first and which enabler has to come later. Now, just talking about industrialization over the last few 500 years, the first industrial revolution, it took place between late 1700s and early 1800, and that was marked by use of steam powered engines and machine tools. Then second industrial revolution came in the start of 20th century, and that was marked by use of electricity industries, which made it more mobile and it increased the overall efficiency. The concept of this mass production and assembly line was also introduced during that second industrial revolution. Third industrial revolution, it came around late 1950s, and it started with the growing use of computer technology and electronics into the factories, which gave more emphasis to digital technology and automation software rather than analog and mechanical technology. Now, fourth industrial revolution, which is a topic for today, it has started just in the last decade, and it is slightly taking its roots to entire manufacturing domain. Now, the main advantage of this Industry 4.0, as already stated, is it helps the business owner to have more control over the business, to develop better understanding of every aspects of the business through access to real-time data, to improve efficiency, increase productivity, and achieve desired growth for the business. And through effective collaboration across various value chain members, it provides altogether new and holistic approach towards manufacturing. Now, talking about steel industry, globally, steel is growing at a CAGR growth rate of around 4% during last 5 years, and India has managed to increase its production at a much higher pace than the rest of the world. If you see, world is slightly going towards EAF technology rather than BF route, and also more emphasis is being rightly given to reduce the carbon footprint and looking for economical viable options for replacement of carbon route. Globally, all steel makers are very much now focused on creating values through product customization, enhancing the utilization of the digital solution, and securing cost-effective raw materials. Talking about India, India currently the second largest producer of steel, around having 110 MTPA of production capacity annually, and the steel sector looks quite promising with because the per capita consumption of steel is growing from almost 64 kg in financial 16 to 74 kg in financial 19, and it has been outlined that the potential lies in per capita steel consumption touch to around 160 kg by the year 2030. So there is a huge potential for growth in steel industry, owing to currently low per capita consumption and looking to the country's large population and the good forecast for India's GDP growth. Now, Industry 4.0 and the enablers which makes the successful rollout of this Industry 4.0 across entire manufacturing value chain. I have done a literature review for different industries, and I have found out through various authors like understanding benefits of Industry 4.0, support and commitment of management, research and development, training and development. These were basic enablers which have been identified by various authors. If you look for some authors, they vouch for development of IT infrastructure and network. Some go for value addition in terms of IoT. Then study done by Briggs and Luthra Mangla, they highlight the role of government policies. Development of synergy within organization is also highlighted by some authors. Then the vertical integration, horizontal integration, and manufacturing system connected to network, which helps in achieving digitalization across the entire value chain, has also been identified by some of the authors. Now, the multi-category decision-making model, that is ISM, which is known as interpretive structure modeling, which has been used to model the enablers. It is a very old technique it was proposed by Warfield in 1973, and over these years, it has gained quite a lot of momentum in solving real-life problems. If you see the barriers of reverse logistics, critical success factors of implementation of advanced manufacturing technology, enablers of Six Sigma implementation, and the level for performance of manufacturing industry, these all have been modeled through this ISM model. So, as I've already stated, that the real problem for today is we have to study, we have to chalk out what are the top 10 enablers and the relationship between each of the enablers and how they have to be successfully rolled out for implementation of Industry 4.0 in steel sector. Now, these enablers have been identified after exhaustive literature review and also after going to focus group discussion with some of the head of departments of steel plant from both private sector and public sector. And now these are the top 10 enablers which have been zeroed down: cyber security, higher management support, operational efficiency, acceptance of employees, government vision and regulation, IoT, big data and analytics, synergy among team members, development of IT infrastructure, innovation in production, and IT training and development to all employees. Now, after we have zeroed down on the enablers, now we need to model it through this ISM modeling. Now, for this, there are some 7 steps which have been identified. The first step already we have zeroed down on the enablers. Now comes the most important step, whereby we have to identify the contextual interrelationship between each of the enablers, how each enabler affects the other enabler. And after doing that, we make a matrix which is known as SSIM, structured self-induction matrix. And from that, we go on to make a final matrix, and then the hierarchical model is developed. Now, this is the SSIM matrix. Here you see all the enablers, they have been identified as VAXO, whereby you suppose an enabler in a cell Ij, if enabler I leads to enabler J, but if both the enablers are not interdependent, then it is categorized as V. Similarly, if enabler J leads to enabler I, but both enablers are not interdependent, then it is categorized as A. Similarly, if both enablers are interdependent, then they are called X, and if both the enablers are unrelated, then it is categorized as O. So after a huge lot of efforts from different stakeholders, we have zeroed down on each of pair of enablers categorized as VAXO. Now this model, it says that for any entry as a V, for that cell Ij, we have to substitute it as 1 or 0, the cell Ij or cell Ji, as the case may be. Similarly for entry A, entry X, and entry O. And by substituting all these VAXO with 1, 0, we get an initial reachability matrix. And after doing the rule of transitivity, we get the final matrix. Now, this model, this matrix, it is then iterated to have an intersection set, and after multiple round of iterations, we get this structural model, whereby the highest level is shown, which is having the highest iteration level, and the lowest is having the lowest iteration level. Here you can see cyber security and government vision regulation is at the bottom of the model. Then there is higher management support. Then at the middle chunk, it is development of IT infrastructure, IoT, acceptance of employees, and training and development. And then it comes operational efficiency and synergy among team members. And finally, the innovation in production, which will lead to successful rollout of Industry 4.0 in any steel plant. Now, based on this model, we calculate a driving power and dependence power. This is also part of ISM modeling, which is known as Big Mac analysis. And here you can see a 4-quadrant model, whereby the first quadrant is called autonomous, second is called dependent, third is called linkage, and fourth is called driving. And it is built upon the measurement of the driving power and dependence power of each enablers. Now, this is very interesting one, which you can see that the first quadrant, known as autonomous, it doesn't have any of the enablers. It shows the power of each enabler. Each enabler is neither weak in driving power nor weak in dependence power. Either they are strong in any one or they are strong in both. If you see the second quadrant, which is dependent one, you see 3 enablers have been identified as dependent. One is operational efficiency, and then is synergy among team members, and then it is innovation in production. These 3 enablers are having high dependence power, but low driving power. Similarly, if you see quadrant 4, there you can see 1, 5, and 2, cyber security, government vision, and higher management support. These are having high driving power, but less dependence power. And then the balance are given as linkages, which are high in both driving power as well as dependence power. Now, in the current study, just now, as I stated, that there were no, in the first quadrant, there was no autonomous enablers, and thus it is evident that none of the identified enablers are weak for successful adoption of Industry 4.0. In the first quadrant, we had this operational efficiency, synergy.
Sorry to interrupt. We are running out of time.
Sir, just last slide, sir. Just last slide. And innovation production, they are weak drivers but have strong dependence. This is the basic reason they are located in the top of the hierarchical model. So, unique contribution for this paper is that these enablers have been modeled through this ISM approach with respect to clarity developed in roadmap for successful implementation of Industry 4.0 in Indian steel sector. The enablers which are at the foundation level, they have to be implemented initially, as other enablers are driven by them. The support from higher management, cyber security, and government vision and regulation, they have to be ensured first for bringing the cultural change, and then we have to proceed to a successful rollout of Industry 4.0 roadmap. Subsequently, based on financial status of the company's development of IT infrastructure, IT training, and exposure of employees.
We can read that. Okay.
Yes.
Please.
So just this was the unique contribution, and the limitation is that we have only taken top 10 enablers and have talked to few of the steel industry players, and modeling also in future it can be further elaborated through big models such as structural ecosystem modeling, ANM, and Demetal. And then we can also get a more clear picture for this Industry 4.0 rollout. Thank you, sir.
Thank you, Mr. Ajeet Kumar, for your insightful lecture on implementation of Industry 4.0, in which you have mentioned about the future scope of value hitting also, as well as the current scenario. Thank you for the lucid presentation. And I now invite Mr. Nitesh Ranjan from Bokaro Steel Plant for his paper on waste management in the steel industry. So, Mr. Nitesh Ranjan, you will please present your paper now.
Yeah, very good afternoon to all of you. I am Nitesh Ranjan, AGM Environment, along with Head of Environment, SAIL Bokaro, Mr. Naveen Prakash Srivastava. So, I am just sharing my screen. So, are my slides visible? Sir, yeah, are my slides visible?
Yes, it is visible, sir.
Okay. A very good afternoon to all of you. And thank you for giving these opportunities for presenting our paper on waste management in the steel industries. So, actually, the steel industry is known for being cyclical and reflective of overall market condition. You know, demand increases during economic boom and it plummets during global recession. So, you know, it's very important for steel industries across the world, especially India, to have a way to counter this issue. I think Naveen Prakash Srivastava is also there. Sir, would like to add something? So, sir, I think he is not getting connected. So, I will continue the presentation. At the end of the presentation, he will give his concluding remark. So,
good afternoon, everyone.
Yeah, Naveen is there. Yeah.
Am I audible? One second.
Yes, sir, you are audible. Please go ahead.
Everyone.
Yes, you are audible.
Okay. A very good afternoon to everyone. I'm Naveen Srivastava, General Manager Environment. And in fact, I'm working as a chairman at Bokaro Center, Institution of Engineer Bokaro Center. At the outset, I would like to thank IEI State Center for organizing such a great event and giving us an opportunity to address such a lovely audience. Many congratulations to the team, State Center. We are deliberating on waste management in steel industry. Ayogyam vastu nasteva. Nothing in this world is waste. Now, time is the only thing we cannot recycle, and rest everything is recyclable. Waste isn't waste until we waste it, and waste is a waste until we know the value of it. Gentlemen, we are the second largest producer of steel only after China. This is a good news and bad news also. Good news is for the steel makers, the consumers, for our nation, for our infrastructural development, but bad news for the environmentalists, for the waste managers. In fact, when the steel industry, our national steel policy aspires to manufacture 300 million tons of steel, we as a waste manager should gear up for utilizing those 150 odd million tons of waste which will generate out of our steel production. Because as a steel manufacturer, our steel fraternity know it very well that for every ton of steel we produce, we get around half tons of solid waste generated. This is a rough estimate based on the raw material and the process efficiency. This is the quantity we assess normally all across the world. It depends on process to process, and industry wise, in fact, the manufacturers also depends on the process. So we are all geared up as a leading steel manufacturer of the country. We are all geared up. We have formulated, chalked out our action plan. And in fact, there were days in 80s, 90s, when a lot of artificial mountains were created nearby all steel major manufacturers. those of BF slag, the LD slag, and the fly ash, because of that, every steel industry used to have this power plant, captive power plants. So lot of waste was generated in those days. There were not much consciousness, no much regulation on the waste management. Now, thanks to the lot of mandates that have come by the Ministry of, they have been formulated by Ministry of Environment for it in form of their environment clearance conditions, consent to operate conditions. All, in fact, the fly ash notification, there were so many fly ash notifications, and we have evolved from 90s to 2020, and we are all set to utilize every ounce of waste being generated from steel industry. Now, gentlemen, we have just prepared a presentation, a very brief presentation. My colleague Nitesh Ranjan will be deliberating on those slides, and at the end of this presentation, we'll be welcoming all the questions, all the from the audience. So, Nitesh, are you ready for the presentation? I'm handing over session to you.
Yeah, sure. Thank you, sir. So, as I was telling that steel is a cyclical in nature and it depends on market condition. So, what is the solution for steel makers? India is going to have target at 300 million ton of capacity by 2030. So, one of the solution is judicious utilization of waste. Either we need to have a secondary market for whatever waste we are going to have, because there was time when steel was not getting sold, but at that particular time the byproducts and various waste product of steel that saved the industry. Similarly, the other way around is to reduce our cost. One way of reducing our cost is to use the various waste that is being generated in the steel industry as an input material in your own plant, so that we can reduce the cost of making the steel. And thankfully, in the last financial year itself, Bokaro has earned a revenue of more than 2,200 crores by just selling this waste. And we are also cutting our cost by utilization of various waste that we are generating, including LD slag as an input raw material at our various sources. For example, recently we have started using LD slag as an input in center plant. We have started using LD slag as a replacement of aluminum in SMS. We have started making briquettes out of sludge, and we are going to charge it in our converter as a replacement of coolant, as a replacement of your raw material, as well as your input material, including iron material. And apart from that, we are also going for this micro pelleting by using various waste across the plant, including ESP waste. And so in that way, we are trying to counter this issue in two ways. First, increasing our revenue by selling waste, and second, using those waste as input raw material.
Hello, your slides are not changing.
Okay. Naveen sir, can you share the slide from
your
end?
Sure, Nitesh, sure.
Naveen sir, please share the slides from your end. Okay. Or I will try it once again, sharing the slide. Okay, is the slide visible right now?
Yes.
Okay, so what I will do, I will just use it in this issue. Okay, so this is the slide that I was talking about. India is you're targeting 300 million ton of steel by 2030, and we are going to have a huge amount of BF slag, LD slag, and waste from.
Because I am also ready. If you're okay, then if you're any glitches are there, then I can.
This is fine. This is fine. Sir.
Okay. That's
so the main issue that the steel industry across the world and India is facing is regarding LD slag, because BF slag we are using it is cement making. So SAIL has done something on LD slag that I am going to showcase. So the first thing that we have done is steam aging of our LD slag, so that we can use it as a rail ballast in railways. And currently it is being used in Bokaro Ispat railway station. So we are using this LD slag, weathered LD slag, as a replacement of rail ballast across our plant. So this is one of the way we have done along with RDSO Lucknow for use of LD slag as rail ballast. Second thing, we are also using this plastic waste in road making, and we were the first steel plant to use biodiesel in our locomotive. And we have also started using LD slag in fly ash brick making. Actually, the cost of fly ash bricks become high because of this cement input. So what we have seen that the ratio of calcium oxide and SiO2 is similar in case of LD slag as well as cement. So we have tried using LD slag in fly ash LD slag brick making, and we have found wonderful results. These were the bricks that we have met from LD slag fly ash bricks. And apart from that, the strength is very high. Strength is very high as far as conventional bricks is concerned. And another initiative we have taken along with RDCS, making this eco-friendly pebble blocks from LD slag of Bhopal Steel plant. And we have also installed this kitchen waste to biogas plant at inside the Bhopal Steel plant. So what we do, we collect kitchen waste across our canteen in the plant, and we are making, we are replacing at least one your commercial cylinder per day at our canteen using this kitchen waste biogas plant, and the manure is being utilized inside the various garden inside the plant. We have also started this experiment of using LD slag as a soil conditioner. One of the issues at Jharkhand is most of the soil in Jharkhand and across India is acidic in nature. So use of LD slag can solve the problem. And recently, SAIL has an MOU with ICAR Delhi for effective use of this LD slag based eco-friendly fertilizer in agriculture, and results are showing it's showing good results. Soon we will have a substantial way of using this LD slag as soil conditioner across India. And we have also used this BF slag for road making. So this air called BF slag, there's a ISI code for BIS code has been given, IS 383, for use of this coarse and fine aggregated for concrete specification. So for making this concrete, we have started using this air called BF slag, and this is the road that has been constructed at RDCS Ranchi using the air cooled BF slag of Bhopal Steel plant. Now, apart from this solid waste, there is also a huge issue of waste heat management in the steel making. So that is one of the aspects that we need to touch, so that we can reduce our overall CO2 emission as well as our overall specific energy consumption. So coke dry quenching, blast furnace top gas recovery, then power generation from sintering waste heat, steel making process from waste heat recovery, and combined cycle power plant are some of the areas where work has already been done for generation of power from waste heat of a steel plant. And apart from this use of proper judicious utilization of liquid waste is also very important. And Bhopal Steel plant is moving towards zero liquid discharge. We have 2 effluent treatment plant, and all our fresh expansion modernization plant is coming with ZLD project. So this in turn reduce our cost of water, as well as our commitment to various statutory body for reduction of our specific water consumption. You can see for LD side, because of various innovation, our utilization has come up to 100%. And this is the waste management what we have done at Bhopal Steel plant. It has touched almost 100%. We have lined up few projects to further enhance it. And this is one of the example where we have used various waste product of steel plant in making gardens. So this is one of the garden at Bhopal Steel plant. So at the end of this presentation, I would like to conclude that the only one of the option that steel industries has to counter this cyclical nature is to converting this waste that are being generated in steel making to wealth. In that way, they would be able to increase their overall revenue, and in the second way, they would be able to reduce their input cost or steel making cost by using the waste as a input raw material. Thank you. That's all from my side.
Nitesh, I would like to add from here. Actually, there was a time constraint, so Nitesh has run their slides very fast. Just to add few lines, because this seminar is basically a national conference is on sustainability in the steel industry. So regarding sustainability, when we think of sustainability, there are a few lines which are coming in my mind. In fact, let us not wait for well to dry to know the worth of the water. And the difference between animals and humans is that animals change themselves for environment, but we as a human change the environment for themselves. This is a very funny thing, and there's irony, and this creates the problem. And our nature provides a free lunch, but only if we can control our appetite. I know these challenges for the environmentalists are big. By 2030,
Naveen ji, we have other presenters meeting. So
one sec.
Sorry, we have to take questions if you want. You can
we permit.
So
yeah,
time is up for you. Please let me allow others. Conclude. You conclude first immediately. please.
I have just concluded, just wanted to conclude with this note that because these challenges are there for the steel industry, for the waste managers, which I was talking in my opening remark. No matter how complex global problems may seem, it is we ourselves who have given rise to them. So they cannot be beyond our power to resolve. So we are all geared up. And in fact, thank you so much to Institution of Engineers for giving us an opportunity to present in front of such August gathering. And our questions are invited.
Thank you. Questions are again, time is up. So we will not be able to take questions. We can discuss later on. So I will ask you to start the next panel.
Thank you, Naveen Saab and Mr. Ajeet Kumar, for this very useful presentation, whereby not only the environment is covered, but also generating wealth from waste. That is very, very pertinent in today's context. And thank you for your lucid presentation. I now invite Shri Nitesh Ranjan. I'm sorry, Shri Shyamji from RDCIS for his paper on carbon capture estimation of teak plantation at Rourkela Steel Plant. Shri Shyamji, please. Shri Shyamji, can you hear me?
Sri Shyamji, can you hear us?
Mr. Shyamji, can you hear me?
Sir, your audio is not working.
Yes, madam, your volume, please up your volume.
Am I audible now, sir?
Yes, you are audible now.
Yeah.
Can we have Mr. Shyamji?
Sri Shyamji, sir, your audio is not working, Mr. Shyamji, because you have been unmuted, but still we cannot hear you. Are you online, sir? Yes. Yes, sir, we can see you have raised your hand, but sir, please check your audio. It is not working.
Madam, do you think we can proceed to the next speaker and then
yes, sir, by that, yes, sir. I am also requesting you that by that time, Mr. Shyamji can control his audio devices, we can take up the next paper, the last one.
All right. So, Mr. Shyamji, if you can hear us, we take up your presentation after this presentation is over. So, I now invite Shri R.S. Sinha and or Shri Harsh Kumar for presenting their paper, Economizing Coke Rate to Increase Efficiency and Reduce Emissions in Blast Furnace Iron Making Plant. Shri R.S. Sinha or Shri Harsh Kumar from Mekon. Please.
Yeah, thank you, sir. I hope we are audible enough.
Yes, you are audible. And
our video is on, sir. Right, sir?
Yes, you are audible and visible.
So my colleague Harsh Kumar will take us through the presentation. So we'll be just be starting in a moment or so. Just a second, sir. Screen share. So is the slide visible, sir, to all of you?
Yes, sir. Yes, please go ahead.
So Harsh will take us to the slides.
Good afternoon to all present here. The topic of our presentation is economizing coke rate to increase efficiency and reduce emission in blast furnace iron making plant. So this is the typical view of the blast furnace, called the heart of the steel making plant. It is, if we talk of what blast furnace is a metallurgical furnace in which the coke and the coal are being charged from the top, and the hot metal that we get is we get from the bottom part of the furnace. So if we see the left side, it's the outside view of the blast furnace, and the right side is the inside view of the blast furnace. So if we talk of the general description of the blast furnace, it is an extremely heat exchange smelter. Why we call it as a counter current heat exchange? Because the coal, coke, ores, sinters are being charged from the top of the furnace, and the hot air and the hot blast is done from the bottom part of the furnace. So there is a counter movement of the materials, and the air is taking place, which in that case the heat exchange takes place. That's why it's called a counter current heat exchanger. As I clearly mentioned in the beginning, that the blast furnace is the heart of the steel plant. So it consumes about 2/3 of the total energy requirement for an integrated steel plants. The degree of the heat utilization is to a remarkable extent of 80%. The capacity of the blast furnace increasing day by day, and in modern high capacity blast furnaces can produce as much as 14,000 tons per day. So this is the Mecon's association with iron making industry in recent past.
Sir, kindly unmute.
So Mecon is associated with like almost all the big steel industries. So the major work we do is engineering consultancy services for like example, we have done it for JSW, AVPL, and for like we have done for a lot of mini blast furnaces. If we talk of the present blast furnace major assignment,
जिनका mic on है वो kindly mute कर लें. Other than the speaker, kindly mute your mic. Yes, sir, please go ahead.
Yes, sir. So if we talk of the present blast furnace assignments we are taking off, we are taking the design engineering and consultancy services for the expansion project of JSW Vijayanagar from 13 MTPA to 18 MTPA, and we are taking design engineering and consultancy services for ESL, for KIOCL, for Jairaj Ispat, Andhra Pradesh, for Bengal Energy Limited. We are doing the EPC project for installation of forge stove for BF4, and we are doing the job for vetting of foreign technology DNE for JSPL Angul. Now talking about the world steel production data, about 70% of the steel production which is done in the world is done through the blast furnace basic oxygen furnace route. But there are many alternatives that was developed theoretically for the blast furnace. That was DRI, Corex, Finex, and many more. But it was like talking of their economical feasibility. It was found out there is no alternative route which is as commercially viable as blast furnace. So if we talk of the climatic effect of the steel making, that is that the 70% of the total steel production, if we talk of it, contributes to the 7% of the global CO2. If we go thumb rule, the thumb rule says that for every 1 ton of steel produced, 1.9 ton of CO2 is emitted. What is the antidote for it? The antidote for the above problem would be we decrease the use of carbonaceous materials that are used in the blast furnace. How can we, if we decrease the carbonaceous materials that are used in the blast furnace, it will lead to the decrease in the coke consumption, and it will consequently result into decrease of the CO2 emission. So if we talk of the thumb rule that I was talking about, for every 1 ton of steel produced, 1.9 ton of CO2 is produced. If we see the distribution in various departments, the raw material preparation has around 0.3, 0.2 and 0.1, and the iron making part has the maximum distribution of the CO2, that is around 1.3%, which contributes to about 68% of the total CO2 that is produced in the integrated steel making route. So if we can control this CO2 which is generated in iron making part, we can control the overall emission of the steel industry. So one of the methods that are used in a blast furnace is PCI. So I'll give a brief introduction of what PCI is. PCI is a process involving in which fine granules of coal is injected inside the blast furnace. The basic aim of this PCI is to increase the efficiency of the blast furnace. The various benefits are also noted here. It leads to the lower consumption of expensive coking coals, which we know is very expensive. Going through the data, it takes about 1.4 ton of coking coal to make 1 ton of coke, which can be replaced by 1 ton of pulverized injected coal. It can also lead to higher BF productivity, that is the amount of hot metal that is produced per day. It also leads to greater flexibility in BF operation. It allows us to control the flame temperature and the thermal conditions inside the furnace, which can lead to the increase in production. It also helps in increasing the productivity of the hot metal and the quality of the hot metal that we get as the output, and controlling the silicon contents inside the hot metal. It can also lead to reduce in the overall emissions from steel plants due to the decreased coke requirements. So these are the bottlenecks of using PCI. That is, if we use high rate of PCI, what are the disadvantages of it? This is listed in this table. The list is like, if we keep on increasing the rate of PCI, it can lead to increase of ore or coke, which can lead to overall increase in intensified gas flow at wall side, or it can lead to inferior permeability at lumpy zone, or it can lead to increased cohesive layer thickness, or it can lead to increased degradation of coal, which would ultimately lead to increase of the heat loss, or accelerated wall damage of the furnace, or inferior burden descent, and increase of pressure drop at upper and middle part, increase of pressure drop at lower part. For this problem, we have a countermeasure. The countermeasure.
Mr. Sinha, 1 minute. Sorry to interrupt. 2-3 minutes left, please.
Yeah, we can speak faster.
Of course, sir. So these are the bottlenecks which are listed in this table. The bottom line for this would be, PCI would be, we cannot replace coke, because the cokes can be used as because the cokes are like a mechanical burden, and they support the furnace, and they are like allow the gases, molten iron and the gases to ascend and descend. So we have alternatives for PCI. The alternatives for the PCI could be H2 injection, natural gas injection, plastic injection, and replacing the coke with renewable, neutral and H2 rich carbon bearing materials. We talk of the H2 injection. As we were going through the presentation, it was said that the H2 is the future fuel which we can use. So what we do here is, along with the PCI, we inject hydrogen here. So how can we inject hydrogen? We use an electrolyzer. What electrolyzer does is, it takes water from the atmosphere, it breaks it into hydrogen and oxygen. The hydrogen part goes into the blast furnace, whereas the oxygen parts goes into the stoves. So if we see the diagram, if we see the graph which is there on the topmost part of the slide, it can lead to the decrease in the top gas temperature. Also, it can lead to decrease in the raft temperature. So if we talk of the modeling part shows that 27.5 kg hydrogen injected per ton hot metal through the tubes is possible without major change in the thermal blast furnace. This is limited due to the operational constraints of blast furnace. But the advantage of it is that it can reduce the carbon emissions by around 21.4%, which is around 0.46 ton CO2 per ton of steel. The second process could be natural gas injection. It was like natural gas is abundantly available, so the specific consumption of coke is reduced, replacement ratio being 1.3, 1.4. It can also lead to decrease in the ash, sulfur and alkalis. So going through the data wise, 50 kg of Ng replacing coal lowers slag rate with 6.4 kg. As slag basicity is increased and sulfur content of slag is decreased, the requirement of limestone and lime is decreased, which reduces the cost of operation for any plant. But the limitation of natural gas is that it has an endothermic effect on the raft. Raft is a raceway adiabatic flame temperature. To compensate for this reduction in the flame temperature, the hot blast air needs to be enriched with oxygen. So the increase in the oxygen contents reduces the nitrogen content, which in final turn causes the top gas temperature to drop. So the bottom line is like carbon requirement for a furnace with 50 kg natural gas injection is 8 kg lower than for a furnace with coal injection. The next injection we can do is through waste plastic injection. As we all know that the waste plastic is very much available in the entire country, so it has been practiced at several blast furnaces.
Please summarize.
Yes, sir. In Germany, Japan. So the problem with waste gas injection is that we require preheat treatment, homogenization, and dechlorization. But the advantages that we have is that the waste is estimated to be 70 kg per ton.
Go to the next slide.
That was the injection methods we can do. These are the indirect methods of increasing efficiency. The first one is BF dehumidifier, which is adopted in the blower that can decrease the water content, which can overall decrease the coke rate reduction by 0.1 to 1 kg. We have dry type GCP, which saves water for us. That is 5 tons of recycled water and 1 tons of makeup water. It also leads to decrease in the power consumption and increase in power generation. So the final and the most modern technology that we are using here right now is the plasma torch. This is in technology purpose. So in graph we can see, just showing the graph, we can see that if we keep on increasing the hot blast temperature here, the coke consumption that we are getting keeps on decreasing and the CO2 consumption keeps on decreasing, because the idea here is just to superheat the hot blast that we are getting. So one more method that we are planning is using alternative burden, like by using the old sinter and the pellet plants, we can have self-reducing old coal briquettes, which is called BREX, and which contains self-reducing iron and carbon. I will cite an example with her data that BF running with burden containing self-reducing BREX 60% compared to a burden containing sinter 70.5% will allow a 30% coke reduction and a 10% reduction of total through fuel rate. But the basic disadvantages is that we require a high top pressure that is around 4.5 bar and a high oxygen enrichment of up to 60%. Which cause for a major overload. So finally concluding the entire slide, we all know the blast furnace is going to be the dominant rule of iron producing, not just in present, but in near future. So we have to develop technologies to use it in the most efficient way that we can. We cannot replace coke, because coke is very important in providing mechanical burden and the inflow of the hot blast gases through it. But we can have various non-coal injection materials such as natural gas, H2 or plastic. We cannot directly use them in the furnace, but we can combine them with various other technologies, and we can use it in a more hybrid way. And steel industry needs to partnership with research institutes and government support to explore new technologies to work on greenhouse gas emissions and lower the dependency on fossil fuels. Thank you, sir.
Thank you, sir.
Thank you, Mr. Sinha and Mr. Harsh Kumar, for that informative presentation on PCI and the alternatives to powdered coal injection, by which we can increase the efficiency of the blast furnace. So that was quite informative. Thank you very much for it.
Thank you, sir.
And now going on to the next presentation, I will now invite Sri C.D. Goswami.
sorry to interrupt you in
Yeah,
between,
please.
sir. I have spoken to Sri Shamji.
Yeah.
He is ready, so we can take up his
Sir,
presentation. Sir.
am I audible, sir? Myself, Samji?
Yes, sir.
Yes,
You are audible, sir.
So
Okay, sir.
we'll start with the presentation of Shri Shyamji now.
Yes.
Carbon capture estimation of teak plantation at Rourkela Steel Plant. So Shri Shyamji, please continue with your presentation.
Okay, okay. Thank you, sir. Now I'm going to share my screen.
Shri Shyamji, please maintain the time limit. As we have seen that many speakers have overshot the time limit. So kindly.
Okay, sir.
Yeah, please go ahead.
Okay, good afternoon, sir. Myself, Samji, working in Energy and Environment Group of RDCS, which is a corporate R&D unit of Steel Authority of India Limited. Sir, my slide is visual.
No.
Sir, I would request you to open the presentation first in your desktop and then share. Please don't share the screen, sir. You select the particular file and then you share.
Okay, okay. Is this visual?
Yes, sir.
Yes. Is it in presentation mode?
Yes,
Not, it is in regular mode, sir. If you want, you can put it in the presentation mode. So you can run your presentation in regular mode also. We can see it. But at present, your screen is visible only. So you select the present PPT file.
Okay. Is this visual?
Not yet, sir.
Is this visual, ma'am?
Yes, sir. It is visible. Please go ahead, sir.
Good afternoon, sirs. Myself, Sabji, working in Energy and Environment Group of RDCS, which is a corporate R&D unit of Steel Authority of India Limited. The topic of my presentation is carbon capture estimation of teak plantation at Rourkela Steel Plant. This is based on work carried out during the period 2014 to 2018 for estimation of carbon sequestration of the tree species Tectona grandis, which is also known as teak, with the help of Rourkela Steel Plant and Tropical Forest Research Institute, Jabalpur. This is the next slide. This is the scheme of presentation. We will go through introduction, then objective, then
Not changing, sir. Not
experimental.
changing. Sir, not changing. Slides are not changing, sir.
Okay. Again, I go to share this. Share entire screen.
Your slides are not visible. So
Yes,
only the screen is visible, sir. You please select the slide PPT file and then you go ahead, sir.
Is this visual, ma'am?
So your screen you have shared,
Yeah.
but on that we can see this panel only. So after clicking the green button, you have to select the PPT file. and then you can make it full screen and you can run your presentation.
Is this visible or not?
It is
I mean, this is in my computer. I'm seeing the full presentation.
But sir, we are not able to see it.
Please read it.
Okay, sir. Going to the next slide. This is the introduction part. So as we will all aware that the concentration of carbon dioxide and other greenhouse gases in the atmosphere have increased over the last few decades and are expected to rise further. Due to natural and anthropogenic processes, carbon has accumulated in the atmosphere at an estimated rate of 4 plus minus 0.2 gigaton carbon per year in the first decade of the 21st century. As we know, tree acts as the vital sink for atmospheric CO2 as they fix carbon during the photosynthesis and store excess carbon as biomass for the long period of the time. Trees are also important carbon pools in the forms of vegetation, deadwood, litter, and soil organic carbon, which continuously exchange CO2 with the atmosphere. As we know, the tree growth, carbon is absorbed from the atmosphere, and as the plant mature, die, and rot, the carbon is released back into the atmosphere. So we can say that the mature forest made up of various aged trees, as well as dead and decaying matter, may be carbon neutral or may release carbon to the atmosphere. Now going to the next slide. This is also the introduction part. However, the gradual buildup of slowly decaying organic material will continue to accumulate carbon in the soil, thereby acting as sink. Trees substantially contribute to carbon sequestration potential of soil by increasing soil organic matter.
Mr. Shyam, we are still not able to see any slides. Have you tried sharing the screen?
Yes, sir.
We are not able to see the slides. Anyway,
stop
please.
sharing, sir. Please stop sharing once and try again.
Okay, okay. I'm going to the share screen button, then share windows, and then my that particular.
Don't share the window, sir. Select the file. Select the file.
You can continue your presentation without slides also. You please continue. Okay, that will be taken care. Okay, please go on.
Okay. Extensive. Now coming to the objective portion, extensive plantation has been rate at RSP over the year, with a purpose aimed at either enhancement of aesthetics, restoration of degraded land, compliance to statutory requirement, making of barriers for air and noise pollution, or utilization of its medicinal, timber, and fruit values, which has resulted in partial or full accrual of all these benefits. In this process, considerable amount of carbon has already been sequestrated over the year automatically. The main objective of this study was a quantitative assessment of the carbon getting captured through teak plantation. Now coming to the experimental part is divided into three sections, which are first development of allomatic equation, then laying of quadrants, and finally estimation of carbon sequestration by the teak plantation. Now coming to the first experimental part, which is development of allomatic equation. A complete harvest method is the most common and precise way to measure the above ground biomass of the tree. This method involves felling and weighing of a representative sample of trees in randomly selected plots, but the process is destructive and time consuming. In this process, not only are the cut tree get removed from the forest, but the felling and extraction process may seriously injure neighboring tree and undergrowth. Hence, non-destructive methods are used to measure the above ground biomass by developing allometric equation. Trees allometry establishes quantitative statistical relation between some key characteristic dimension of trees, usually easy to measure like diameter, girth, and other properties often more difficult to assess like volume and mass. on the basis of detailed measurement on a small sample of the typical tree. Now coming to the next slide, sir. Height and diameter or girth at breast height are the most important predictor of biomass, as a strong correlation exists between above ground dry biomass and both tree diameter and tree height. Height has been incorporated in many equations, but it is very difficult to measure height in closed canopy forest. Diameter at breast height or girth at breast height is the easy measurable, consistently reported and highly correlated variable with biomass. Allometric statistical regression equation for Tectona grandis under Archela condition was developed between one of the growth parameter like girth at breast height and carbon content in the trees. For doing this, 8 numbers of teak trees of different girth classes ranging from very young to full mature tree were selected and cut. Geo coordinates and diameter at breast height of each tree was measured before felling. Then the cut tree were separated to different components like main bore, which is a main wooden axis of tree located between the base and the crown. Then branches, which is woody material of the tree crown up to a minimum diameter of 1 centimeter, and leaves and twig with a diameter less than 1 centimeter. Sample of the all cut tree were freshly wetted and brought to the laboratory where these samples were oven dried till the reading become constant. The below ground biomass of the tree and the carbon content of the tree was assumed to be 1/4 of its above ground biomass and half of its dry biomass, respectively, as per norms of International Panel on Climate Change, 1996. Then graphs were plotted.
Sri Shyamji, kindly proceed towards conclusion because we have only 1 minute left.
Okay, sir. The last portion is the result and conclusion. Annual carbon sequestration has been quantified with the difference in carbon stock assessment of vegetation of 2 consecutive time periods, that is between 2014 to 16 and 2016 to 2018. Here 2 tables are given. First give the average growth data of the teak tree, and second give the average carbon sequestration per tree per annum. In first time period, that is in between 2014 to 2016, 3.46 kg of carbon per tree per annum were sequestrated. In terms of CO2, 12.69 kg of CO2 were sequestrated per tree per annum. Similarly, for the next time period, that is 2016 to 2018, 5.47 kg of carbon per tree per annum sequestrated, and in terms of CO2, 20.06 kg of CO2 per tree per annum sequestrated. This is the conclusion, sir.
Thank you, Shyamji, for this informative and unusual presentation. But definitely this carbon capture estimation of teak plantation will go a long way in reducing the environment pollution as well as aesthetics and air and noise pollution, as rightly pointed out by you. I now invite Shri C.D. Goswami for his paper on innovation in clean and green steel making for sustainable development. Shri C.D. Goswami, sir.
Namaskar, Ajay Saab or Das Saab. Really, at the end of the session, I know the lunch time has reached, so I don't want to give you or rather bore you for much time. You tell me at what time I have to conclude. Simply, I'll conclude it. Reach to the last slide. I will slides here.
Sir, you can proceed for the next 12-13 minutes.
Yeah. Okay. So our I think hello.
Yes, sir.
Your getting it, no? And
Yes,
I am audible
you are
also.
audible as well as your screen is
Sir,
visible.
I am audible. Yeah,
Yes, sir.
and I am audible. Okay, no problem. Thank you. So if you see our technology as such concern, I am very focused on innovation and as well as development of clean and green steel. Now, this up from the adopting best available technology up to the capacity utilization, these are all conventional. And breakthrough technology is the upcoming focus that is being focused here. Now, if you see, I'm not going to say rather much here, only 2-3 slides I will focus. First is cause, if you see, it is mainly we are having a limited resources, both natural resources as well as we are having mineral resources and environmental concerns, especially global warming. And pathway, it is the ecological footprint reduction and industrial symbiosis, skill development. These are the main focus. Now, why climate, we say, why climate change? Why climate change? Now you understand, still yesterday we are focusing carbon dioxide in the main, or rather when the problem is here. Now actually if you see carbon dioxide, if you analyze, he is the oxygen generator and the source of carbon dioxide. If you see instead of carbon dioxide, how oxygen concentration varies, it varies from 35% to 12%, and somewhat we are lucky, we are in the region of 20% oxygen level. And water and carbon dioxide, these are the two main sources for an ultimate energy source is solar energy. And pre-emitted atmosphere and volcanic age, it is all the same atmospheric composition. Now, why your global temperature is rising? It is because sun rays is falling, and normally if it is a white surface, it's 95% energy is going to be reflected. Unfortunately, gradually the surface due to the ice melting, it is changed into black and maximum energy is being absorbed. So this is the root cause you can consider. And that's why when global warming increases, it is further, it is a vicious circle of global warming. Now, I'm not going to focus much on this slide. Only one thing, our national target is by 2030, 30 to 35%, we have to achieve from 2005 base level. Now, as we know, our national steel policy aims at 300 million ton of steel production 2030, and we have to all gear up for that. Now, how the production varies to see. There you can see one good point in 2020 that our import has reduced by 40% and our export has increased by 20%. This is no doubt a good, and one tension area, that is a capacity utilization gap. That means if capacity is there and if it is not, production is not achieving, that it is underrated, so it is not acting at duty point. So inherent there is an inefficiency on the system. Now, this is the root, or you can say focus of decarbonization. Carbon, that is the coke, which has called maximum C content. That is more about 88% or 85% of carbon content. Whereas hydrogen has nil. And similarly, electrolysis has got a nil carbon content.
Sir,
and as we know,
slide change नहीं हो रहा है सर. सर आपका slide change नहीं हो रहा है सर. Please sir.
Are you getting me? हाँ?
सर आपका slide
change नहीं हो रहा है.
ना नहीं सर.
Okay. Change नहीं हो रहा है.
नहीं सर. Please sir. सर.
ओ तब तो मेरा ख्याल से आज स्लाइड के चक्कर में नहीं जाना है. अगर नहीं हो रहा है तो मैं ऐसे ही बताता हूँ भाई. I don't want to waste your time. It is a lunch time. And I think madam has got these slides. I have already shared. Madam, Aparna madam.
Yes sir, please tell me.
I think I have shared my presentation to you earlier, as because I was knowing this sort of problem will come. Is it in your mail? It is available. If it is available, you can slide. So
let me check, sir. Just give me a couple of seconds.
Yeah. In the meantime, I'll not stop. I'll continue because time is a focus. I understand.
Sir, आप एक काम कीजिए ना. This is Praveen here, sir. नमस्ते.
हाँ, बोलिए.
सर उसको ना फिर दोबारा शेयर कर लीजिए सर. The problem will be sorted out. एक बार बंद करके ना, you just share again. And if it is not running, then you operate it in standard mode. Then your problem will be solved. And now it is moving, sir.
Okay. Now it is moving. Let me see.
Now better share again, sir. We don't see your this thing. Start sharing.
Okay. Okay. Now is it visible?
Yes, sir. It is visible, sir.
Yes.
So as such, you can say decarbonization. When now it is visible, no?
Yes.
Yes, sir.
Yeah. Now it is moving also.
अभी तो move नहीं कर रहा है, sir. Not moving now.
अच्छा. तो ऐसे करते हैं, मैं स्लाइड शो में नहीं आ रहा है.
Sir, if you want, I can also share your presentation, sir.
Please, madam, you please share it. So I think it will be good, and I don't want to waste time.
You please continue. I am sharing it.
Please. So what I want to focus, there are, as we know, the Fe2O3 say oxygen we have to remove. That means oxidation number of Fe from +2 to +3, it has to be reduced to elemental form, that is 0. That means we need some electron towards that, so that it can meet the requirement. That this reduction can be made by conventional chemistry group. We have straight carbon, C. Otherwise, another is hydrogen or electron. If we feed to Fe +2 or +3, it will reach to Fe. Now, if we see, coal is in between. After coke, it has got more hydrogen content. Further, it is better in case of syngas. Natural gas, CH4, it has got further more hydrogen content. So it is giving benefits for decarbonization. And ultimate aim is hydrogen. Similarly, if we can go a electrolysis, which is a recent research is going on at Boston Metal, and then mainly MTI is doing, MIT, that is MIT Institute is doing the research. So by that, there is a focus towards that. So these are the ultimate fundamental research is going on. If we see Indian steel plant, why our energy is increasing? Last,
is it visible to all?
Your slide is visible?
Sir, the slide is visible, but it's not moving.
Concern for energy saving. Madam, you please share your slides.
Sir, I have shared. Is it visible?
It is visible, but it's not moving. It's stuck at the slide number 1.
But I have changed it.
I am now in slides. You can say I am after the triangle slide. Next slide, I am here. Concern of energy savings. Okay.
Okay, sir. Let me check.
Could it be reached? If it is not able to share, no problem. I can simply say.
Sir, is it visible now?
Yes, slide number 9 is visible now.
Yes, concerns.
Yeah, very correct. Slide number 9. That way I focus. Okay.
Concerns of energy saving.
Correct. You are very correct. So, हम अगर देखें mainly Bhilai steel plant, our SiO2 content, it has increased more than 5 years in last 10 years. So 5%. And similarly is the case of alumina. So these two are the culprits for energy consumption increase and slag quantity is increased. So waste is being taken out, or rather sensible heat is being taken out by the slag. And another thing I would like to say, whatever scrap we are using, if we are not processing properly, that it needs another 25% positive energy. Next slide. This is being internationally focused, how research step is moving, and bandwidth wise these things are. As on today, our level is 2.3 to 2.5 ton of carbon dioxide per ton. See, if you see current opportunity with all the measures, what has been discussed, CDQ, TRT, whatnot. So we can achieve up to 1.9 to 1.8. R&D opportunity, say they are the ferrochrome, what Mr. Sinha has right now told. So this is a burden material, and Japan is working on that. Said we have topped this. We can achieve up to 1.54 to 1.6. Maximum theoretically we can reduce with the carbon or blast furnace technology up to 60% theoretical minimum. अगर हमें net zero होना है, then we have to have a H2 base reduction or electrode exchange. And if at all carbon dioxide is generated, then we have to capture it and utilize this. That is CCUS. So there are inherent tension is also there. This may from the safety point of view. So this I am not going to focus. This has been. So if you see how our focus point of the energy saving, slide number 12, madam. So here what we want to say, only one point I want to focus here. That is a dry gas cleaning plant. Our Anand ji's first half mein bole hain, and international, Nippon has already developed it internationally, and MR Kumar bhi bole hain, already he has told that JSW is implementing. So similarly, it is an upcoming opportunity. Whatever the modernization is coming, whether it is sale or whether it is a private plant, we should focus ESP based both gas cleaning plant for BOA, basic oxygen furnace, as well as blast furnace, correct? And other things are nothing much, circular economy or what TRT, everything is well known to you. So I don't want to. Next slide, I want to focus, madam, that is 13 number slide. If you say, we have already told our target is 33 to 35% reduction. तो हमें पहुंचना है 2030 तक 2.01. अगर business as usual practice चलेंगे तो we'll be at 2.3. So हमारा अभी जो cumulative CADR, cumulative annual decrement rate is 2%, minus 2%. And our demand is we have to achieve 2.3%. So for this achievement, what are the breakthrough technology? What are the innovative things we have to do? Before that, I would like to say, if we introduce hydrogen-based plant and not taking care of energy efficiency possibility, then it's useless. Until unless we harness all our energy efficiency possibilities, then only we think about hydrogen. Now, one thing I must say, what last presenter also said, biosequestration. Ministry of Environment has focused minimum 33% of project area has to be green belt development. And nowadays, mainly for the public sector plant, what are the balance area is there in a township, even up to 40% green belt development is a focus area. Now, this is I am now on slide number 15, madam. Slide number 15. This is a NSP, that is National Steel Policy. And if we can see our target is being focused that we have to match to the coke rate of somewhat 300 to 350, CDI to a 180 and 200, blast furnace productivity 2.5 to 3, and specific energy consumption 5 to 5.5 gigajoule per ton. You will be happy to note Indian plants are already achieving. Tata Steel has claimed already 5.7 your energy consumption. CDI is already 204. So it is nothing great. We have to further move. So our aim is we have to go to 1.8 to 1.9. One thing I must say here, the slag rate, it is totally dependent on the mineral quality. That means a God gifted RINL, why they are producing only taking 287 kg of blast furnace slag? Because they are getting good quality of iron ore from NMDC. Unfortunately, our sale plants are not getting somewhat raw material quality of Tata is good. Madam, this I want to focus is R&D, long-term measures. If we have to have, then we have to focus on R&D. This is, madam, this is a very important slide, or this 17, that all we know, scrap recycling policy 2019, it has been developed. And here, principally, it has come a 6 hours policy. 6 hours matlab, not only 3 hours, इसमें 6 hours ले आए हैं, and इसमें फायदा ही फायदा, win-win situation, both from the water side as well as energy side. Water तो हमें consumption घटेगा 40%, and energy it will reduce 85%. Other benefits already told earlier. Now, international level, where we stand. See, India, our scrap consumption is a good point. In 2018, it was 25.6%. Now in 2019, because before data are not available in web as well as ministerial figure, it is 27%. Whereas हम देखें अगर international level में best अगर scrap utilization में देखें, so this is Turkey. Turkey is about 82% they have achieved. And हमारा जो steel imports, that has also increased in 2019, 6.3 to 7.05. And good, one thing you can note, the European Union तो steel भी अच्छा है, rather scrap भी they are recycling as well as they are exporting also. 50%, 49% they are exporting. And our America is exporting, USA is exporting 17%. We have to develop a long way on our recycling process. Already started on the. Now, why we are calling steel is a green material. If you see, if we compare with aluminum, it is a non-magnetic. So we cannot simply separate it out. But if you talk about steel, here tramp element are less compared to aluminum. Aluminum has got 13 number of tramp elements, which is impurities. और स्टील में है only 6, लेकिन इस ट्रैम्प एलिमेंट सबसे खतरा है, इसीलिए हमारा सेकेंडरी स्टील is not performing up to the mark. They are not able to achieve the required quality of market. Now carbon fiber, what is our Ministry of Highways is already focusing, Gadkari Sahab is focusing the carbon fiber को use करना है. लेकिन carbon fiber so far technology इसमें incineration के अभी तक it is yet to be developed. Okay. Now, this is a very, that bottom, that slide number, what I want to 20 number. Dynamic modeling revealed that until and unless we allow our tolerance to increase more scrap, tolerance to as gas recycling to be downsized by 50% by 2005 due to high copper content contamination. That means tramp element copper is very dangerous for steel quality, and it cannot be used in automotive seals. इसीलिए virgin steel is required. That's why the DRI and blast furnace has to be there for maintaining a quality steel. Otherwise, we have to have developed in the steel making technology. Already international research is working, especially if we can wear a high speed casting. Then impregnated impurities in small quantity, it is acceptable, and by that we can maintain the quality. So this is the mainly, I don't know whether any student is there in this forum or not. So I want to focus it for the young engineers. देखो भाई, what we want to say, innovator का एक courage होना चाहिए. All this old people experience is required, but until and unless you have the courage to fail, you cannot success. So that's why only 3.5% people can think of innovate, then all possibility they will fail. Second time, third time, they will succeed. So this is a very important on the adoption cycle. And those who are early adopters, they will be also surely success. In life also you'll find this is a very important subject. So we have to work along with the younger generation. This is a carbon sequestration, what has been focused. The carbon dioxide के नीचे डाल देना है, लेकिन अगर इसको utilization करना है, that means whatever the entrapped gas is there, we have to enter through the holes so that entrapped gas will come out or oil will convert. It is USA, it is called EOR, that is extended oil recovery. But there is a problem. If through the impregnated layer, carbon dioxide leakages, and carbon dioxide is heavier than air, then it will be dangerous for the living element, because ultimately we will not be able to respire. Now, as we have told about hydrogen too much. This is next slide, that means slide number 23. So this short analysis has been done. Here, one thing only I would like to say. This is the ultimate way, whether we like or not. जैसे गीता धर्म है, ultimately system will take care of the things. हम चाहे या ना चाहे इसको correct रास्ता में system will force us to implement hydrogen. So that is the way out. And इसमें सबसे जो हमको cautious होना है about the hydrogen is a real dangerous point from risk and safety and explosion hazard, because its flame is not visible, but it has got lot of energy. So with all precaution, we have to introduce. And that's why hybrid technology has also come in a big way. You can see, Ambassador साहब पूछ रहे थे कितना cost difference आएगा hydrogen में. Abhi hybrid has told it will cost 25% more. अगर स्टील बनाने के लिए if you say hydrogen steel बनाने के लिए 2633 किलोवाट आवर चाहिए, एंड अगर ये से मैं स्टील बनाता हूं उसमें 816 किलोवाट आवर ले लेते हैं, मतलब 30% वहां पे गया. अभी ब्लास्ट फर्नेस के लिए as you know 70% एनर्जी कंज्यूम. So as far as carbon dioxide concerned, it is a break-even point with the conventional energy, because आज हमारा देश में और इंटरनेशनल सर्वे किए हैं from CDM, it is 48 ग्राम पर किलोवाट आवर में कार्बन डाइऑक्साइड जनरेट होता है. And left hand side, it is a what has been told by our also Tata's people, that is Hisrana technology. It is a blast furnace technology. And that right hand side, we are focusing on the hydrogen generation and hybrid process, and ultimately we are reaching. But इससे भी और आगे बड़ा एक चीज आ गया, that is Boston Steel, what I was talking. MIT has developing, and mainly their focus is on European Union, Europe, as well as Canada, Australia, so that they can directly melt the iron ore and then electrolysis, so that by the process of electron, what I have told, they are reducing it and getting a pure metal. So in between, hydrogen is removed. So by this ultimate aim, their energy consumption will be raised. So this is the Hisrana already explained by, I need not to further explain, but Tata has told on this. Now, what my earlier friend has told, carbon sequestration, ministry demanded for ISP Kanpur, what is the possibility of carbon sequestration. So international research, sir, what we have papers are, we have reached somewhat 22.6 kg per tree per year. So, sir, we have reached, I know your lunch time, it is important, but only thing, Mitra sahab ka ek point मैं clear करना चाहता हूँ. Last question he has asked, what will be the pressure drop in case of dry GCP? Dry GCP, there are two types. One is blast furnace based, one is bag filter based, another is ESP based. ESP based pressure drop is very less. Across ESP, pure ESP, it is only 30 to 50 millimeter of water gauge. Across, considering inlet and outlet, piping and ducting, it will be 250 millimeter of water gauge. And in case of bag filter, it will be somewhat 250 to 300 millimeter of water gauge. But upcoming days, only we have to go for ESP, because there is bag filter, there is a maintenance problem. So overall, another thing, about 10% due to sensible heat content of heat content of the dry gas, it will produce 10 to 12% more energy in the TRT. So with this, I'm ending, sir. Thank you.
Thank you very much, sir.
Thank you, sir. Thank you, sir.
Though we have overshadowed, but I was engrossed with your lecture or with your presentation, sir. It was nice to listen to you, sir. Thank you very much. So we'll conclude this session, and we'll move to, we have to rather report to Institution of Engineers. So with the conclusion, the presentation by Mr. Ajeet Kumar and Kumud Ranjan was nice one. They have talked about the energy and energy savings and all. And rightly they have talked about the all the environment, economy, and society, the three pillars which is to be taken care. And then implementation of Industry 4.0 is equally important for us to digitize the operations, and that will serve the efficiency, will improve the efficiency of the steel making, and indirectly it will reduce the sustainability, increase the sustainability also. Then the waste management was one of the most important topics which our BSL Bokaro, Nitesh Ranjan has talked about, and Mr. Naveen Srivastava has talked about. That was one of the most important area where we have to concentrate, and we have to utilize 100% of waste. Mostly we are utilizing. As on date, we have gone up to 80%. So balance we have to take care. And then capture. Then the carbon capture by RDCS. That was a nice presentation, research topic on which they have shown that how the by teak plantation they have reduced their potential of reduction of carbon generation, carbon capture. Then economy of coal, coke rate, Arish Sinha and group from Macron have they given. They are also to the point that we cannot get away with the coke, but we have to increase the fuel injectants to have the efficiency, greater efficiency. Then comes our Goswami Sahab presentation. It was a nice one. It was a great one. And we have learned about the how the ultimate solution is we have to go to hydrogen-based plants, whether we like or do not like. So that is the ultimate goal, and we have to proceed in that direction. It may take time. A lot of research is required by the academia and industry consultants. In India, what I have observed that still we are not having any contact between the industry and the academia. So this area and consultants, so this area is required, this area of interaction is required to improve the uses of waste or use of hydrogen. So hydrogen has to be green. We are using not many hydrogen. We can go ahead, but we has to be slowly and slowly we have to move to the green. But at present we can start with the blue, brown, any gray, any hydrogen is welcome at present. Okay, thank you very much, everybody, and thank you much for listening to us. And let us join at Institute of Engineers, I think. Okay, thank you very much. Thank you.
Thank you very much, sir, for nicely coordinating the session. Thank you very much. Now I would request Jharkhand State Center to take over and initiate the valedictory program.
ये भी बंद है सब कर दिया चलिए
Good afternoon. क्या जा रहा है? Good afternoon. I, on behalf of Executive Committee, extend a very warm and hearty welcome to you all in the valedictory session of 34th National Convention of Metallurgical, Material Engineers and National Conference on Sustainability and Steel Industry. I especially welcome Technical Session 1 Chairman Sri Somesh Biswas, Dr. Technical Session 2 Chairman Dr. Madhadhar Devta, Principal Scientist IIMT Bhubaneswar, Chairman Technical Session 3 Dr. Ambasta, Chief General Manager Macon, Ranchi, Technical 4 Session Chairman Engineer Ajeet Kumar, Chief General Manager Set Cell Ranchi. I also welcome Engineer Eli Sekhan, Rapporteur of Session 1. Senior General Manager, Inverter Engineering, Macon. Engineer Nitish Kumar, Rapporteur of Session 2, General Manager, Macon. Engineer M.R. Kumar, Sir GM, Macon. Rapporteur of Technical Session 3. Engineer S.K. Das, Rapporteur of Technical Session 4. I also welcome who are here offline and online also. ये कन्वेंशन और सेमिनार बहुत सक्सेसफुल रहा, इसमें कोई शक नहीं है। इसके लिए वेलकम के साथ साथ मैं सबका स्पेशल थैंक्स देना चाहता हूं, स्पेशली हमारे बीआईटी मिश्रा के जो वाइस चांसलर साहब थे, उन्होंने हर तरह का हम लोगों को हेल्प किया। उसके साथ साथ डायरेक्टर टेक्निकल अग्रवाल साहब, अरोरा साहब और जितने भी हमारे साथ आए और सबों ने इस टेक्निकल जितने टेक्निकल से सब कुछ कामयाब बनाया, बहुत अच्छा हुआ। हम सबों के बहुत बहुत शुक्रगुजार हैं, जय शुक्रिया अदा करते हैं। साथ ही साथ हम स्पेशली मैडम अपर्णा दत्ता जो हेडक्वार्टर सेल से कंडक्ट कर रही हैं, उनके भी स्पेशल थैंक्स देना चाहते हैं। इन सब के साथ again I welcome you all in this very active section. Thanks. Now I request our chief guest of the very section, Shri Ajeet Kumar Sahab, to kindly take over, please.
Good afternoon to all the participants and delegates who are attending this 34th National Convention on Metallurgical and Materials Engineers Conference. In fact, we had very fruitful discussions all these 2 days, and I was told that more than 20 papers were presented during these 2 days, and more so, everybody was concerned about the problem which we are facing for the steel industry. As we all know that steel industry is the major source of creating environmental hazards. And as we know that we are planning for enhancing our steel production from present 120 million ton to 300 million ton by 2030, and the carbon dioxide emission is definitely going to increase by 4 to 5 folds, which is really concern for all of us. And I request all the engineers and the people who are working for the steel industries to make a note of this, and the R&D personals, R&D engineers should devote time on this. I also request all the organizations who are involved in steel production to look into this and create a good R&D fund to come out with a solution. Because what I heard yesterday and today, that everybody is concerned about the greenhouse gas emission, and which is increasing. Now, the per capita income, per capita steel consumption today is only 74 kg per person here. But as we grow, by 2030, the per capita steel consumption is going up by 160 kg. That means the consumption is likely to increase. But my concern is that nobody talked about the requirement of iron ore and coal. Suppose we are planning to increase our steel production to 300 million ton. What is going to be the iron ore requirement? That is not less than 550 to 600 million ton. And also the coal production is also right to increase. So these are the two major areas where actually we have to look into, so that at the time of production of iron ore, the environmental hazards also should be looked into. And more so that we have to take care of the quality concern of iron ore and coal also. Now, before I conclude, because this is a concluding function and everybody is probably hungry and it's a lunch break almost. And I would like to congratulate all the speakers and the persons who conducted this, all these sessions, to come out with a very good suggestions. And definitely we are going to compile the recommendations and we will further deliberate on it. This is not the end, this is the beginning. And I also would like to congratulate the chairman of this conference, Mr. A.K. Saxena, the chairman of Jharkhand chapter, Mr. Alam, the secretary of Jharkhand chapter, Mr. Manoj Kumar, and also the organizers who organized this program very successfully. The concerns were very, very well deliberated, and those are to be taken forward. One very important aspect which I always used to advocate is the interrelationships and working together, the academicians and the industries. Yesterday, it was a very good move to get the Vice Chancellor of BIT Mesra, and he also assured us that there will be interactions with the industry, because I personally feel that whatever the industries are doing, the institutes are all not aware, or whatever the institutes are doing, the industries are not aware. So there should be link between our institutes and organizations and industries. With this, I would like to conclude, and also would like to thank for giving me this opportunity to share my thoughts. And also I would like to congratulate the Jharkhand chapter for organizing such a good conference. Thank you very much.
Many, many thanks, sir. Now I'll request Engineer Raj Sekhan, Senior General Manager, Environmental Engineering, Macon, to give a brief about the technical session.
Good afternoon to all participants. Respected Chairman of the Convention and Chairman BOG, Engineer A.K. Saxena ji, respected Chairman Jharkhand State Center, Alam ji, respected A.K. Kosh ji, who was ex-CMD of HEC, and respected Honorary Secretary, Jharkhand State Center, Manoj ji, and all my dear friends. I am thankful to Institution of Engineers for giving me this opportunity. And in the first session, there were 5 papers. Out of the 5 papers, one of the paper could not be presented because the author was on travel. And I hope that in future might be the paper would be presented, and I believe that this paper would be appearing in the compendium which will be published by institution Jharkhand State Center. The first paper was titled Steel Industry, the Decarbonization Imperative. This was supposed to be presented by Dr. M.P. Sukumaran Nair, and he was Director, Center for Green Technology and Management, and formerly he was Secretary to Chief Minister of Government of Kerala. And we hope to hear his speech in the next forthcoming programs. The second paper was titled Efforts Towards Meeting Sustainable Development Goals in Steel Industry Through Zero Waste Mining and Resource Optimization. This was presented by Engineer Kumud Anand, who was from Mecon Limited, and it was authored by Engineer Arun Kumar Agarwal, who is the Director Technology Mecon, along with Engineer Kumud Anand AGM Mecon, Palash Banerjee AGM, and Anand Barduraj. So, keeping the time limit in mind, I would only read out the recommendation given by this paper. That is, special emphasis should be given to zero waste mining methodology. Zero waste mining methodology is nothing but during mining, whatever the iron ore or the coal which is mined, apart from the ore which is going for the industries for the production of steel or for any other process, the other waste like fines or anything which is generated by beneficiation should be recycled with modern advanced technologies, and it should also find its way towards the production of iron and steel. So this emphasis was there, and as of now there are 120 million ton of unutilized iron ore fines lying in different mining areas, and he recommended that we should go for a lot of pelletization plants with beneficiation, and then it can be routed through many process technologies like DRI, electric arc furnace, and so on, with consideration of sustainable energy requirement and recycling of all byproducts. I would not call it as a waste. All the byproducts should find its way back into the system so that we end up with productive iron and steel. And he was also telling that the coal which is mined has got, as of now, has got a lot of ash content, which is not finding its way in the coke ovens. And the operability becomes difficult in coke ovens, and the productivity yield also reduces. So the paper recommended that we should go for a lot of coal washeries, and then the ash content should be reduced, and accordingly coking coal should find its way to the coke ovens. While putting the washeries, we should also see that all environmental measures should be taken care, and no waste effluent or any sludge from the coal washery should find its way. And these effluent treatment plants should be adopted with zero liquid discharge concept. Later, he also emphasized that low-grade iron ore and high-grade coal needs to be beneficiated and utilized by improving the quality of iron and reducing the ash. This was the first paper. Second paper was on beneficiation studies on Donamalai iron ore slimes to recover iron ore concentrate for sustainability of iron and steel industries. This was presented by Dr. Raghupati Rooney Bhima Ravji. This was his research which was done in the CSR laboratory. He was a former CSR chief scientist, IMMT Bhubaneswar, and he is also the council member and of the chemical division, IEI. Dr. Raghupati emphasized that whenever we are going for any beneficiation system, that the testing has to be made, and accordingly it should be blended, for which he gave certain equations wherein the standard size of balls in the ball mill is to be utilized, and by running the test we have to derive at a particular size which is can be adopted, and accordingly the mill has to be designed and then utilized so that to save energy, so that sustainable blending, sustainable beneficiation can be taken. And this recommended that there should be always some research studies, and it was a nice paper also. The third paper was from from Tata Steel. Tata Steel, wherein a lot of recommendations were given by Dr. Himsmi Jamil Hussain. He talked about all the 17 sustainable goals which need to be adopted and its agenda points, and then forming strategies, and then bringing in social development. It is not only the industries. He emphasized that the business should be such a way that the society should also get benefited, and the business will be a sustainable development. And they also emphasize that on the biodiversity, wherein Tata Steel has brought the first biodiversity park wherein butterflies are being harvested there. So it is a welcome thing. And the fourth paper was by Bilal Steel. They also emphasized on certain measures which need to be followed, wherein energy has to be recovered in a very nice way. I just read out certain points. That is, there is a change energy consumption pattern. That is, we need to import, use imported heat, bioenergy, green energy, efficient use of materials. Bilal Steel also told about increasing the life of the building so that indirectly we can reduce the steel consumption, and then we can indirectly reduce the emission of CO2. And they talked about the best technologies to be adopted, and in practice the best recovery is there, CDQ, TRT, and we have to also look into modern technologies like green fuel to be used other than coal being the prime, so that we can reduce the carbon dioxide emission. So these are the four papers. I thank these presenters of the papers, and then it was a nice learning for me. And I take this opportunity to thank my chairman of the session, Mr. Somesh Biswas, who introduced the speakers very nicely, and he also made the path for the presenters nicely. I also learned from him a lot. Thank you, sir. Thank you very much. Thank you to institutional engineers.
Many thanks, Rajakshan Saab. Now I request Nishit Kumar, Nishit Kumar, Senior General Manager, Mecon, to kindly brief the technical session 2. Please.
Good afternoon, all the participants who have joined online, and office holders of Institute of Engineers Jharkhand chapter who are present in the office here. I would brief you about the papers presented in technical session 2. There were 5 papers planned in this session, out of which 4 were presented. The first paper was presented by Mr. Nitesh Ranjan of Bokaro Steel Plant, which was on emerging technologies for decarbonization and energy efficiency in steel industry. The second one was presented by Mr. Prabhas Ranjan Behra of IMMT Bhubaneswar, and the topic was a sustainable technology to produce green and clean steel by hydrogen plasma smelting reduction. The third paper was presented by Mr. Anupam Chaudhary and Arka Datta of Mecon Limited, and the topic was determining the roadmap to reduce carbon emissions. The fourth one was presented by Mr. Ajeet Panigrahi of IMMT Bhubaneswar, and the topic was effect of SI content on phase transition temperature, microstructure, and hardness and medium manganese steel. All the papers basically stressed on the ways to reduce for decarbonization and energy efficiency in the steel industry, and the basic premises which were discussed were the ways how we can reduce this, and some of the ways which were discussed were hot charging in rolling mills to contain the latent energy of latent heat energy, use of EAF route to use of scrap, and then carbon capture, internal carbon piercing was also discussed, and to reduce carbon emissions, use of solar energy, and phase down instead of the importance of phase down instead of phase out of CO2 emission was also stressed. In all, the papers in this session were quite well presented, and I think will go a long way in improving the environmental concerns which the steel industry faces today. Thank you.
Thanks a lot, Ajeet Kumar ji. Now I will request Engineer M.R. Kumar, Senior Engineer, Mekong Achi, to give a brief in technical section 3.
Good afternoon, sir. Chairman Saab, Ajeet Ghosh Saab, Alam Saab, Saxena Saab, and Honorary Secretary Manoj Kumar Saab. This technical session 3 has 6 papers. Altogether 6 papers were presented. The first paper was augmentation of coking coal for steel sector. See, the paper actually emphasized about the blending of indigenous coal thing for making a coke ovens. So they have identified, the presenter identified the importance of blending and the endeavors of Coal India Limited and BCCL. So how they are putting coal washeries and increasing from presently 20 to 25% blending to increase more than 32, because Tata Steel is doing about around 32% blending with the stamp charging coke oven batteries. So that is the gist of the paper number 1. The second paper is energy recovery through TRT, because this is the one of the technology which is used for the energy recovery. The furnace which is having top temperature, top pressure of more than 3 kg presently designing the large blast furnaces, and the operating pressure is only 0.08 to 0.08 kg per cm square. So the pressure which is available in the BF gas will be expanded in a turbine. It will be generated the power, which will be utilized in BF complex itself. Around 50% of energy that can be saved by installing this TRT. That is the gist of this paper, second paper, that is from Set Sail. The third paper is a very good paper, that is on a circularity as a solution. See, that is paper is presented by Tata Steel. So what Tata Steel they have emphasized is, think mantra is the only circularity, because there are 3 things which you can get. The things is reduce 38% consumption of materials, and greenhouse gas emissions can be reduced by 44% by using the circularity management, and 40 lakh crores economies are we can economic benefit can be derived by using this circularity as a system by 2050. So what the paper is also emphasized about what Tata Steel was doing, because they have emphasized about scrap recycling, 68% they are recycling, and they have installed a Hisarna plant, because this is a worldwide steel plant, but that is one is working in Netherlands. Presently they are also planning to start from India also. There are 4R strategy also they are following. So with this, Tata Steel is doing a circularity management, and at the same time they are also going ahead with other sustainable development activities. The third paper is, the fourth one is exploring the potential role of hydrogen in the Indian steel sector. This is done by Terry. This was very good paper, sir. They have given it. This is basically not a technical paper, it is analytical paper. They have given all economic data, usage of hydrogen, what is the benefit of things. This is the one of the good paper which is having the data, so that you will find out, like, can we go ahead with hydrogen injection, or what extent we can go there. And they are saying that $1 to $2 per kg of hydrogen is the requirement. So that should be reduced below 1, so that it can be sustainable to implement hydrogen injection. So that is the one of the paper outcome. Presently it is $5 to $6. By they want to, if it is $1 to $2, then it is feasible to use that. That's what the paper tells about. The fifth paper is improving process efficiency and equipment reliability in coke oven byproduct brand. This is from ISP Banpur, sir. The coke oven byproducts which are extracted in the coke oven gas. So there are they have made very elaborate improvements in various equipments. say tar storage tank. They have changed the tar storage tank. They are cleaning that. That is the first time they did in ISP Banpur. And electrostatic precipitator, they changed some MOC, metal of construction. And there is an automatic sulphate plant is also, ammonia sulphate plant is also there. They have made betterment, the nozzles they have changed something. So these are the developments what they have done in the ISP Banpur. They have elaborately presented. The last paper is sixth paper, that is a sustainable technology to produce green and clean steel by hydrogen plasma smelting reduction. The paper is presented by Dr. Behera from IIMT Bhubaneswar. So they have told like from this 10 kg scale to 100 kg scale में कैसा हम उसको expand करेंगे. So they made a experimental thing. They have presented also. So this hydrogen injection का एक बोल रहा है सर कि plasma hydrogen, because that product is byproduct is only water. So that's what they are saying. This is the one of the technology we have to develop. So there they are telling microwave H plasma and experimental details procedures also they have incorporated in their presentation. These are total 6 papers presented in the third session, and very nicely they have presented. And thanks for the chairman also, DK Ambastasab, Chief General Manager of Macon, who has chaired this session. And thank you. This is the report of the third session.
Thanks a lot, Kumar Saab. Now I request Shri Engineer S.K. Das from CellSet to kindly brief on the technical session 4. Shri Das Saab.
Good afternoon, Alam Sahab and respected members of the Institution of Engineers and my colleagues. Today's session 4 comprised of 6 papers. The first one was put up by Shri Jayant Mandal and Shri Kumud Ranjan of Macon, which pertained to sustainability of iron and steel industry. In this paper, he has presented regarding the sustainability pertaining to 3 important aspects. That is the environment, the economy, and the society, which are the 3 pillars of sustainability, because we have to care for all the 3 in case we have to go on for sustainability of the iron and steel industry. Then he explained about the 8 parameters of world steel sustainability indicators, which were of course related to these aspects, the 3 pillars, that is environment, economy, and society. And he also explained in this paper, rather they explained in this paper, that the steel industry consumes a lot of energy, and therefore it is also energy consuming as well as one of the largest emitters of carbon dioxide. And the raw material costs are about 60 to 70% of the cost of steel making. So it is required that in order to sustain the environment, beneficiation technology and pelletization are very important, because the fines that are generated tend to pollute the environment as well as create an unnecessary burden which must be utilized. He also informed that slag use for cement and zero liquid discharge are important in order to sustain the industry. And for this, he explained about the new technologies for steel making to eliminate carbon emission. Also, logistics and infrastructure is a big constraint for sustainability, which must be improved in order to make this industry efficient. The second paper was very technical in nature, that is related to the implementation of Industry 4.0 for sustainability in the Indian steel sector, which was presented by Shri Ajeet Kumar of Macon. In this, he explained that the Industry 4.0 is also called the 4th industrial revolution. He mentioned about the 4 revolutions starting from the 1800s and went on to the current industrial revolution, whereby it consists of smart factories, wherein optimization,
customization, flexibility are required for overall efficiency and thereby to achieve the desired growth through overall control. An overview of global steel vis-a-vis Indian steel was also presented, wherein the scope for implementation of Industry 4.0 with respect to the world steel scenario was put up, where he showed that there is a huge potential for improvement in the Indian steel scenario. Then he explained about the process of modeling in implementation, and for this, the top enablers for Industry 4.0, that is cyber security, higher management support, Internet of Things, acceptance of employees, synergy, and IT infra development and information and communication technologies are the top enablers for implementation of Industry 4.0. The third paper was related to waste management in the steel industry, which was put up by Mr. Nitesh Ranjan of Bokaro Steel Plant. And he mentioned about the challenges that are related to the waste management because of the resource depletion, the rising energy demand, and the environmental care. It is very important that the waste should be gainfully utilized. He explained about the various utilization methods of this waste generated in the steel plants, whereby he indicated that the use of LD slag as a rail ballast is being carried out. Then the plastic waste is being used in road making. The LD slag is also used as a part of the fly ash bricks, which gives extraordinary strength to the bricks, as well as utilizes the LD slag, which otherwise would have remained as an idle, as a liability in the plants. Then he informed that in Bokaro Steel Plant, they are also doing, they are utilizing the kitchen waste from the canteens to generate biogas, which is again being used as a fuel in those canteens itself. LD slag can be used as soil conditioner because of its nature. And he said that this is also being carried out on an experimental basis, whereby it has given good results. Waste heat recovery is one of the aspects by way of reheating of the gases that are used as fuel, and the top recovery turbine of the blast furnaces. So that by these methods, he explained that waste management in steel industry is very, very essential and is the need of the hour. The fourth paper was by Mr. Shyamji of RDCIS and his team, which was about carbon capture estimation of teak plantation. Now, this is a unique topic which was put up in this workshop, because normally, teak plantation and all these things are somewhat removed from the normal aspects that we discuss. But by teak plantation in Rourkela Steel Plant, the experiment that they have done, in addition to having a huge environmental impact by way of carbon capture, there are the advantages of aesthetics, then also reduction in noise pollution by virtue of these plantations, the gain of timber and wood. So all these aspects he pointed out, and this can be utilized as a very useful tool in order to reduce these pollution and gainfully gain advantage. The fifth paper was related to economizing coke rate to increase efficiency and reduce emissions in the blast furnace iron making plant. This was by Mr. R.S. Sinha and Mr. Harsh Kumar of Mekon. First, of course, he has given the general description of the blast furnace, and then he informed that the blast furnace consumes 2/3 of the total energy that is required in a steel plant. So there it is very important that coke rate must be economized, because it constitutes a very important part of the energy consumption of the blast furnace. And for this, PCI or powdered coal injection was explained by him in detail. The benefits of the powdered coal PCI and the bottlenecks in the usage of PCI beyond a certain limit was explained in detail. There were some alternatives to PCI, which he has mentioned, the alternatives to PCI and their advantages, such as hydrogen injection, natural gas injection, and also plastic injection in this blast furnace route. Then blast furnace dehumidifier, dry type GCP, and plasma torch can also go a long way in economizing the coke rate to increase the efficiency in the blast furnaces. The sixth paper was Innovations in Clean and Green Steel Making for Sustainable Development by Shri C.D. Goswami, who is an ex-Mecon officer. He explained the cause and the resources and the environmental concerns, which are I mean, the concern of the century for clean and green steel making, because the climate change is one of the reasons why we have to focus on green steel making. The capacity utilization is important, because if the capacity is not fully utilized, then the waste capacity the capacity that is wasted goes in towards pollution of the environment. Then he mentioned about the innovative technologies, that is hydrogen-based plant, how we can utilize hydrogen for green steel making. Then the steel scrap recycling policy of 2019 was also explained, because steel scrap recycling is a very, very common trend in the Western world, but so far we have not been able to utilize it to the full extent, and it needs to be brought in, because steel is one of the products which is recyclable a number of times, and still, I mean, the properties do not go away. So this is one point that he mentioned, in addition to touching upon the e-waste management process, electronic waste management process. So these are all the 6 papers that were presented in this 4th session of the workshop. And I thank the session chairman, Shri Ajeet Kumar, Chief General Manager of CET Ranchi, and all those who participated in this seminar. Thank you.
बहुत बहुत धन्यवाद दास साहब। अब मैं जो असल ये जो हमारा सेमिनार या जो कन्वेंशन या कॉन्फ्रेंस जो हुआ, इसके सूत्रधार हमारे सक्सेना साहब हैं। ये सबको मालूम है कि शुरू से ही आखिर तक उन्होंने मेटिकुलसली प्लानिंग किया, मिनट टू मिनट प्रोग्राम बनाया, एवरीथिंग ही डिड। एक्चुअली उनके बगैर ये हमारा प्रोग्राम कभी सक्सेस नहीं होता। तो उनको हम उनके बहुत बड़े हम आभारी हैं और धन्यवाद देते हैं। साथ ही साथ उनके लिए सर रिक्वेस्ट करेंगे कि सर आपके लास्ट वर्ड सर आपके लिए सर। नहीं सर 2 मिनट सर, बिकॉज सर विदाउट योर लास्ट वर्ड दिस कन्वेंशन विल नॉट बी कंप्लीट सर, दिस कन्वेंशन विल नॉट बी कंप्लीट।
Thank you, Alam Sahab. And it was a team effort and we did it nicely. And many thanks to BIT Mesra, Vice Chancellor, Joyjeet and his team that they made the inaugural function very memorable. I understand the registered participants were 252. And yesterday inaugural, we were more than 60%, more than 65 people were there offline present. Leave aside the supporting staff. So in today's context, this was a very successful inaugural and a successful program. Some of the papers which have been presented are par excellence. The one with Terry presented, some from Mecon, some from SAIL, some from other places, even Tata Steel's place, circular economy and other things. They have been excellent papers. We will try to bring out a volume, both in soft and hard, in about a month's time. We are trying to organize funds so that we can go ahead with that and prepare a document which will, along with recommendations. The recommendations we will finalize in next few days, which will be submitted to the chairman MMDB. And thank you, special thanks to Mr. K.K. Mehrotra, the past chairman of MMDB, on whose request or his desire
we organized this national convention. Thank you all once again, and we will put on the recommendations as requested by Aparna in due course. Thank you so much.
Now I will request our Honorary Secretary Sri Ajeet Kumar ji to propose vote of thanks.
Good afternoon, everybody. I think there's been a series of thanks to all the event managers by dignitaries and organizers. Anyway, since it's customary, so in continuation with inaugural function, I would say very vibrant inaugural function, for which we are thankful to Vice Chancellor B.I.T. Misra and all who worked effortlessly to organize the event. Thank you, B.I.T. Misra, for this. And going ahead with the technical session, which started yesterday, and when we are reaching today to come to an end, we are coming to an end. We have here our chief guest, Engineer Ajeet Ghosh, who took out time to chair the concluding session. It's our privilege. Thank you, sir. Thank you, sir, very much to be here. And just saying thanks to a person will not be enough. So let's clap with a big applaud to the person who was the force behind, and he will be forced behind organizing such events. He is none other than Engineer A.K. Saxena. We all have enjoyed the technical sessions, and this was well organized. I would like to thank all chairmen, Engineer Biswas, Engineer Devta, Engineer Ambasta, Engineer Ajeet Kumar, for chairing the sessions very efficiently, making it very lively. I'd like to thank all deputies, Engineer Raj Sekran, Engineer Nishit Kumar, Engineer M.R. Kumar, Engineer S.K. Das, for conducting the session, and also briefing about the session who missed out. I would like to thank our headquarters, and in particular, Aparna Madam, who throughout remained with us to make this event very successful. Would like to thank our chairman of Jharkhand State Center, staff of the center, and all people who got involved themselves under the guidance of Saxena Saab, under the guidance of our chairman Alam Saab, to make this event very successful, went on peacefully without any hindrance. So with this, since I am not a metallurgist, but one thing I really enjoyed, and which got supplemented, like when our eminent engineers, panelists, they were talking about use of hydrogen, how this is going to improve the pollution reduction in the steel industry, and there are other methods and all that. There were so many papers presented. I tried to capture some of the points, but coincidentally, today in the newspaper, there was a photograph that our transport minister, I would say still very young, Gadkari ji, Honorable Minister Gadkari ji, he came to Parliament yesterday in a car which was powered by hydrogen. So see, look at this. It's not only steel industry we are focusing at. I think our steel makers will be striving hard to reach the goal. And the days are not very far when we'll be also contributing to buying hydrogen powered car and coming on the road. So with this, I thank everybody who could make this event very successful and very peaceful. Thank you very much. Jai Hind. Okay, requesting everybody to rise for the national anthem. Jana Gana Mana Vinayak Jaya He Bharat Bhagya Vidhata Punjab Sindh Gujarat Maratha Dravid Utkal Banga Vindhya Himachal Yamuna Ganga Uchchal Jaladhi Taranga तब शुभ नामे जागे तब शुभ आशीष मांगे गाए तब जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय 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 Jai, 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 Jai. Thank you.